Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science drifts gently between wonder and rest. Tonight, we're looking up together at a sky that seems calm, but hides more stories than we could ever tell in one lifetime. Every small point of light you see up there, every glimmer that reaches your eyes from the distance of unimaginable ages, is a sun. Not a star like the ones in fairy tales, but a real sun, burning and alive, holding its own planets close in invisible loops of gravity. Our sun is just one of them, one of hundreds of billions scattered across the galaxy, each with the potential to cradle its own system of worlds. It's strange, isn't it, to realize that the word solar system used to mean only ours. The sun, Earth, and the familiar 8 planets lined neatly like marbles on a classroom diagram. For most of human history, that was the entire known universe. Everything beyond it, everything outside that fragile boundary of sunlight, was simply sky. Now, when you look up, try to imagine that each point of light might have its own Earths, its own moons, perhaps its own watchers. Somewhere out there, under another star's glow, there might be oceans that shine at twilight, or mountains that never see day. But before we lose ourselves completely among those distant orbits, take a moment to notice where you are right now. Maybe you're lying in bed, maybe a soft light glows beside you. The room is quiet. Outside, the night stretches on. Wherever you are, this is your little corner of the galaxy. A quiet planet circling an ordinary star suspended inside a spiral of 100 billion suns. If you find comfort in knowing how vast and strange that is, if this helps you slow your thoughts and feel the soft pull of sleep, you can always give this space a like or share it with someone else who might need a little peace tonight. It helps this calm curiosity reach others drifting through the same stars. Our story begins with a simple thought that isn't simple at all. How many solar systems are in our galaxy? It sounds like something we could just count, like shells on a beach or lights in a city. But the truth is we've only just begun to see them. For centuries, we didn't even know they existed. The idea that other suns could have their own planets was whispered more than proven. Philosophers guessed, poets dreamed, and astronomers squinted through early telescopes hoping to see something move that shouldn't. They found moons around Jupiter, phases of Venus, and rings around Saturn. But beyond the sun, no planet would show itself. For a long time, the universe seemed to belong to us alone. Even so, the question stayed. Were we unique, or was our solar system just one pattern among many, repeated across the Milky Way? Imagine ancient observers staring at the stars from dark fields, wondering if those tiny lights had their own Earths. They had no instruments, no space telescopes, just curiosity and the long patience of the night. Centuries passed. Science grew restless, building better eyes, sharper tools, larger mirrors. And then, finally, the question began to answer itself. The first planets beyond our sun revealed their presence not through light, but through motion. A tiny wobble in the dance of their stars. It was like noticing a dancer shift slightly off step because of an unseen partner's pull. Those first faint wobbles told us something extraordinary. Other solar systems were real. But before we go further into discovery, let's pause to understand what a solar system really is. At its heart is a star, born from a cloud of gas and dust that collapsed under its own gravity. Around it, leftover material flattens into a thin, rotating disk. Inside that spinning mist, small clumps grow into larger ones, dust into rocks, rocks into worlds. Some become gas giants, some stay small and rocky, some may never form completely, drifting as comets or asteroids. It's a quiet chaos that takes millions of years, but from it emerge the ordered families of planets that orbit in steady harmony. The sun and its planets are one example of this process. one that played out among countless others scattered through the galaxy's spiral arms. The Milky Way itself is vast beyond easy imagining. About 100,000 light-year across, a soft pinwheel of stars wrapped in dark dust and silent matter. If you could travel from one end to the other at the speed of light, it would take longer than all of human history. In that swirling city of suns, astronomers estimate there may be between 100 and 400 billion stars. Some are old and dim, others young and bright. Some drift alone. Others come in pairs or trios, orbiting each other in graceful patterns. And the quiet revelation of the last few decades is that most of them, perhaps nearly all, have planets. Our solar system, once thought to be rare, may actually be the rule, not the exception. Think of that for a moment. If even a small fraction of those stars host planets, then the number of solar systems in our galaxy alone could stretch into the hundreds of billions. We're talking about more planets than grains of sand on Earth. Worlds circling every kind of sun imaginable, cool red dwarfs, blazing blue giants, gentle yellow stars like our own. Some orbit so close that a year lasts only a few days. Others are so far away that their suns are just bright spots in an eternal twilight sky. There may be planets of ice and metal, of rock and vapour, planets where rain falls as glass or iron, or where the clouds glow with lightning that never ends. And yet, for all their strangeness, they follow the same universal rhythm of gravity and motion. Each system a kind of celestial clock, keeping time with its own heartbeat of orbits. When astronomers first began to look for these other systems, they had to be clever. Planets are small, faint, and easily lost in the glare of their parent stars. You can't just point a telescope and see them. Instead, scientists looked for hints, tiny dimmings of starlight when a planet crosses in front of its star, slight tugs that make the star move in a regular pattern. From those patterns, they could infer the presence of planets even when they couldn't be seen directly. Each discovery was like hearing a faint knock from across the universe. Somewhere out there, another system existed, unseen but real. As the data accumulated, it became clear that the galaxy was teeming with these hidden families. Some stars had one planet, others had many. Some planets were larger than Jupiter, others smaller than Earth. A few even orbited two stars at once, bathed in double sunsets like the ones from our science fiction dreams. The more we looked, the more common they seemed, and yet the number remains uncertain, because for every system we find, there are thousands we can't yet detect. It's like standing on a dark shore, watching the faint reflections of distant lanterns and realizing that for each one you see, countless others flicker beyond the horizon. The question, how many solar systems are in our galaxy, doesn't have a final answer yet, and perhaps it never will. But the best estimates suggest that nearly every star has at least one planet, and many have more. That would mean there are at least 100 billion solar systems in the Milky Way. Think about that next time you see a clear night sky. Every star you can point to, every faint shimmer, could be the centre of its own miniature universe. Some might have 10 planets, others only one. Some might be barren, others rich in moons and rings and storms. It changes how we see ourselves, doesn't it? Once we were the centre of everything, now we're one orbit among countless others. Yet that realization doesn't make us small. It makes the universe vast enough to hold all the wonder we can imagine. What's remarkable is how calm all of this feels when you think about it slowly. The galaxy isn't a noisy place. Stars move in silence. Planets turn without sound. Light travels patiently, year after year, across the void to reach us. There's a serenity in knowing that somewhere, millions of years from now, another civilization might look up and see our sun as just one more quiet spark among many. They might wonder if it too has planets. They might even guess correctly. The night sky, which once seemed like a random scattering of stars, is now a map of potential homes, each one with its own story of formation, its own age, its own balance of light and dark. If you could somehow fly past them, you'd see that every solar system is different. Some are chaotic, with planets tumbling close to their suns. Others are graceful, with wide, slow orbits. Some might still be forming, young worlds swirling in dusty disks. Others might already be fading, their stars cooling into quiet embers. Each system is a snapshot in time, a different chapter of the galaxy's history written in orbits and light. All of this brings us back to a quiet truth. Our solar system isn't special in its structure. It's special to us because we're here, because we live within it. But to the galaxy, it's one of billions. That's not a loss of meaning, it's an expansion of it. When you fall asleep tonight, you're resting on a planet that's part of a cosmic pattern stretching farther than the eye can see. The Milky Way is a garden of suns, each one nurturing its own worlds in the dark. Some might bloom with life, others may have only dust, but they're all there, circling patiently, unseen but certain. The next time you step outside on a clear night, look up and let your eyes adjust. The faintest star you see could have planets orbiting right now, moving through their seasons, unseen but real. The light that reaches you might have left that star before humans even learned to write, before the first fires were lit in caves, and yet, across that gulf of time, here you are receiving it. You and that distant sun are connected in a simple, elegant way, through light, gravity, and the quiet rhythm of the universe unfolding. It's humbling and strangely soothing to think that while you breathe here on Earth, other planets are spinning through their nights and days under alien skies, some close to their stars, some so far that dawn never comes, and every one of those systems, every orbit and shadow, adds to the great unspoken number that answers our question. How many solar systems are in our galaxy? Enough to fill every dream we could ever have about what lies beyond. The search continues. Telescopes keep watching, their mirrors cold and patient, gathering faint whispers of light from stars that could each be the centre of another world story. We keep counting, not to find an end, but to understand our place among them. The more we discover, the more we realise how little we've seen. But that's the beauty of it. The universe isn't meant to be finished. It's meant to be explored slowly, gently, with a sense of quiet awe. And as you lie there, letting these thoughts settle like dust in sunlight, you can imagine that out there, somewhere in the galaxy, another world is turning under its own sky. Maybe its inhabitants, if they exist, are wondering the same thing. Maybe they're looking up, counting their own stars, feeling the same pull of curiosity and calm. The galaxy is vast, but wonder is shared. The same physics that guides their planets guides ours. The same light that touches them touches you. In that sense, the Milky Way isn't just filled with solar systems, it's filled with connections, invisible, mathematical, and profoundly human. And so, as the night deepens and the thought of sleep begins to settle, remember this: the galaxy doesn't hurry. Stars are born, planets form, and time stretches calmly across billions of years. We're part of that rhythm, a small note in the grand harmony of orbits and light. The question of how many solar systems there are might never have a final number, but perhaps that's the point. It's not about reaching an answer. It's about recognizing the vastness around us and feeling peaceful inside it. The stars outside your window tonight are not strangers. They are neighbours, distant but connected, each with its own solar family circling quietly through the dark. And somewhere among them, our sun glows, a single light in a city of 100 billion homes, holding us gently in its orbit as we drift through the galaxy, dreaming of all the others yet to be found. When we look at the night sky, it's easy to forget what those tiny lights truly are. They seem so distant, so still, like small holes poked into a dark curtain. But if you could peel that curtain away, you'd see that every dot is a blazing world of its own, enormous and alive, burning with the energy of fusion. What we call stars are really suns, not symbols or ornaments in the sky, but nuclear furnaces, each one releasing more energy every second than our entire civilization has ever produced. For most of human history, we didn't realize this. The stars looked too small, too cold, too far to be anything like our sun. To ancient eyes, the sun was a golden god in the sky, warm and near, while the stars were mysterious candles scattered beyond reach. It took centuries of patient observation, of mathematics, and eventually of telescopes to understand that the stars are suns, and our sun is one of them. The same kind of star that hangs above distant worlds we can't yet see. There's something quietly humbling in that realization. The sun, which feels so personal and familiar, is not unique. It's one in a crowd of hundreds of billions, just another point of light when seen from far away. If you could step outside the galaxy and look back, you wouldn't be able to pick it out at all. It would blend in with the rest, indistinguishable from its neighbours. Our entire solar system, every planet, every moon, every orbit, would fit into a single pixel of light in the grand picture of the Milky Way. But inside that faint speck, everything we know and love exists. The light of our own star is the glow that sustains us, but to someone else, in another system, it would look like just one more distant sun. For thousands of years, the stars were uncountable mysteries. People watched them rise and set, move across the seasons and vanish with the dawn. They became the measure of time, the map of direction, and the language of myth. Farmers planted by them, sailors steered by them, civilizations shaped calendars and temples around their motions. But even as we mapped their patterns, we didn't understand what they truly were. The ancient Greeks believed stars were fixed to a giant celestial sphere that rotated around Earth. Medieval scholars thought they might be holes in the heavens letting divine light through. Some early astronomers suggested they were distant suns, but it was a guess without proof, an idea both wonderful and terrifying. Because if the stars were suns, then the universe was much larger than anyone could imagine, and our world was no longer at its centre. That idea gained quiet strength with time. As telescopes improved, the stars began to reveal themselves as objects, not decorations. They shimmered differently. Their colours hinted at temperatures. Their patterns hinted at motion. Slowly, the illusion of a static sky broke apart. The stars weren't fixed at all. They were moving, drifting, orbiting through space, each with its own path and purpose. Our sun too was not standing still. It was part of the dance, circling the galactic centre at hundreds of kilometres per second. The whole sky, once thought eternal and unmoving, became a living system in motion. It was as if the universe itself had drawn a slow, deep breath. When scientists began to measure light more carefully, they discovered something extraordinary. The colour of starlight carries information, a kind of cosmic fingerprint. By studying how light spreads into a spectrum, we can tell what a star is made of, how hot it is, and even how fast it's moving. Through this, we learned that stars are made mostly of hydrogen and helium, the simplest elements in the universe, fused together in their cores under immense pressure. The sun, the stars, and everything in between share the same chemistry. That realization erased the last sense of separation between us and the night sky. We aren't looking at foreign lights. We're looking at kin. The same physics that fuels our sun fuels every other star. The same elements that make our bodies once drifted inside stars that lived and died long before the Earth formed. Every star you can see with your eyes alone belongs to our galaxy. That's about 6,000 or so visible under perfect conditions, though in reality most of us see only a few hundred through city skies. But beyond that faint horizon are hundreds of billions more, invisible to the naked eye. Many are small and faint, like red dwarfs. Stars cooler and dimmer than our Sun, but far more common. Others are massive and brilliant, burning through their fuel quickly before collapsing or exploding. The diversity of stars is astonishing. Some are so enormous they could swallow our entire solar system. Others are barely bigger than planets. Yet each one, no matter how large or small, plays by the same rules. Gravity pulling in, fusion pushing out, a perfect balance that keeps them shining. The idea that each of those suns could have planets is still relatively new. For most of human history, it was pure speculation. People imagined other worlds because it felt right that they should exist, not because they had evidence. Philosophers debated whether the universe was infinite, whether it contained other Earths, or whether we were the single exception. When telescopes grew strong enough to show the moons of Jupiter, the conversation changed. If other planets had moons, maybe other stars had planets too, but proving that was another matter entirely. It would take centuries more of quiet watching before the first hints emerged. Before we found planets, we found movement, a star that wobbled ever so slightly, as if something unseen were tugging on it. That wobble was the first whisper of another solar system, invisible but real. The discovery came in the late 20th century, but the idea had been brewing for much longer. Each step in astronomy built upon the last: better telescopes, more precise measurements, a clearer understanding of light. It was as if humanity had been peering through fog for millennia, and suddenly the mist began to thin. The universe was not a field of solitary suns, it was a community. Once we realized this, the way we thought about the galaxy changed completely. Imagine the Milky Way as a vast spiral of light, a collection of billions of stars orbiting a dark, massive core. It's easy to picture stars floating alone, scattered randomly, but in reality the galaxy is a structured system. Stars tend to form in clusters, born together from great clouds of gas. Over time, those clusters spread apart, scattering their children through the galaxy, each star carrying with it any planets that may have formed. These families of suns and planets drift through space, weaving between spiral arms, circling the center like slow-moving leaves caught in a vast invisible current. When astronomers map our galaxy, they don't see a simple disk of stars. They see layers and textures, thin arms wrapped in bands of dust and gas, regions glowing with newborn stars and older, quieter zones where stars like ours spend their lives. The Milky Way is about 100,000 light-years wide, but only about 1,000 light-years thick. If it were shrunk down to the size of a dinner plate, the thickness would be no greater than a sheet of paper. Yet inside that thin slice of space, nearly all the stars and solar systems of our galaxy reside, each one a sun surrounded by planets, moons and debris, spinning quietly in its own little orbit of existence. Some parts of the galaxy are crowded with stars packed close together. In those regions, night skies would be far brighter than ours. Imagine standing on a world where a dozen suns glow at once, each casting its own shadow. In other places, stars are sparse, separated by light-years of darkness. A planet there might spend its nights under a sky nearly empty of stars, its sun a solitary lantern in an endless void. Both extremes exist in the same galaxy. The diversity of environments is staggering, and yet each follows the same quiet laws of physics. Gravity binds, light travels, and time moves forward, indifferent to distance. As we look outward, we begin to see that the stars themselves are only part of the story. Around them lies dust, fine, dark material that absorbs starlight and hides what's behind it. These dust clouds are both veils and cradles. They block our view, but inside them, stars are born. Over millions of years, gravity draws the dust together until it becomes dense enough to ignite nuclear fusion. The star is born, and the leftover material begins to form planets. This is how solar systems begin, not as sudden creations, but as slow evolutions of matter. Even now, somewhere in our galaxy, New suns are being kindled while old ones fade away. The galaxy is always changing, always alive, even if we can't see the motion. To think of every star as a sun is to change how we imagine our place in the universe. The night sky stops being a flat surface and becomes a landscape of depth and distance. The nearest star beyond our sun is Proxima Centauri, a red dwarf about 4 light-years away. It's close by cosmic standards, yet its light still takes over 4 years to reach us. That tiny delay means we never see the universe as it is, only as it was. Every star in the sky is a message from the past, its light travelling through time to meet our eyes. The farther we look, the further back we see. When we gaze at the stars, we're looking into history. Among all those suns, patterns emerge. Stars come in families bound by gravity. Binary stars and pairs that orbit each other are common. Some have 3 or more companions, creating systems far more complex than ours. Planets in those environments follow strange paths, tugged by multiple sources of gravity. Nights and days would be unpredictable, seasons unstable, skies ever-changing. Yet even there, harmony exists. Nature finds balance in chaos. Every system, no matter how complicated, settles into its own rhythm. When astronomers say the galaxy is filled with suns, they mean it literally. Each one is a potential solar system. Some may be barren, others rich in worlds. Many will remain forever hidden from our instruments, too distant or too faint to study. But statistically, the numbers are staggering. If our galaxy contains around 400 billion stars, and if most have planets, then there could be hundreds of billions of solar systems, each with its own arrangement, its own history, its own potential for life. It's a number so large that it almost defies imagination, and yet it's real, grounded in observation and mathematics. We've only begun to glimpse the variety. Some planets orbit extremely close to their stars, completing a year in less than a day. Others are so far away that they take centuries to circle once. Some systems have giant planets that migrate inward, scattering smaller ones along the way. Others remain neatly spaced, locked in gravitational harmony. The architecture of solar systems is as diverse as snowflakes. No two are exactly alike, yet all follow the same rules. In every corner of the galaxy, the same laws of physics sculpt the same kinds of beauty. Our understanding of these suns and their families continues to grow. Each new telescope expands our reach. Each new discovery reshapes our expectations. We found planets where we didn't think they could exist, around pulsars, white dwarfs, and even stars on the verge of dying. We've learned that planets are not rare accidents, but natural outcomes of star formation. Where there are stars, there will almost always be worlds. That simple truth changes everything about how we see the cosmos. And so, as you listen, and perhaps feel your mind drifting gently between thought and rest, picture this: a galaxy not of cold, distant lights, but of countless suns, each surrounded by its own invisible dance of planets. The night sky is not empty, it's full, overflowing with systems we haven't yet seen, with orbits unmeasured, with possibilities uncounted. When you close your eyes, imagine the soft hum of 1,000,000 worlds circling their stars, moving in silence through the galaxy's arms. Some of those worlds may be shrouded in clouds, some bathed in light, some frozen, some blazing. All of them part of a vast, intricate pattern, a web of suns, planets, moons, and dust, stretching across 100,000 light-years. You, right now, are living inside one of those systems. Your star is the sun, your planet the Earth, your orbit one among billions. Every heartbeat, every breath, every passing moment unfolds under the light of a star that shares the sky with billions of others just like it. The galaxy is not somewhere else. It's here, surrounding you, holding you within it. Every direction you look is filled with suns, even if most are too faint to see. The next time you step outside and catch a glimpse of the Milky Way arcing across the night, remember that you're not just looking at stars, you're looking at other solar systems. Some are ancient, some newborn, all connected by the same cosmic fabric. The sky full of suns isn't a metaphor. It's the quiet truth of our existence. We live in a galaxy saturated with light, each star a story, each one a home. And though we can't yet count them all, we can feel the weight of their presence, their patient glow across the dark. They are the silent witnesses to everything that has ever been and everything that will ever be, shining steadily as we drift through the infinite neighbourhood of stars. For a long time, the night sky was a mystery that refused to give up its secrets. People could chart the movement of the stars, track the moon's rhythm, and follow the wandering lights we now call planets, but the spaces beyond were unreachable. The telescope brought the heavens closer, but even then we could only see light, not the worlds that might orbit those distant suns. For centuries, the dream of other solar systems lived mostly in imagination. There were theories, hopes, and sketches of what they might look like, but no proof. Earth was the only known world, our sun the only known star with planets. Everything beyond was speculation, and speculation, no matter how poetic, isn't science. Yet the idea never disappeared. It lived quietly at the edges of astronomy, whispered by those who believed that the universe couldn't possibly waste all that space on one system. It seemed too extravagant for nature to create hundreds of billions of suns and give planets to just one. There were philosophers who insisted that life must be everywhere, and skeptics who thought Earth's conditions were too unique to repeat. Both sides had their reasons, but neither had data. Science needs evidence, and the universe is not quick to reveal it. The story of how we finally found other worlds begins not with giant telescopes, but with patience. To detect a planet around another star, you have to notice something almost invisible, a tiny shift in light, a faint change in position, a subtle signal buried in noise. The planet itself is too dim to see, drowned in the brightness of its star, but its presence leaves fingerprints. Every time a planet circles its star, it tugs slightly on it. The star wobbles just a little, back and forth. That wobble can be measured if you know how to listen carefully enough. For decades, astronomers searched for such wobbles. They pointed telescopes at promising stars, recorded spectra, and measured every subtle change in colour and movement. It was a slow and uncertain process. Some thought they had found planets, but the data didn't hold up. Others thought the signals were noise. The technology wasn't quite ready. But the idea that other stars might host their own planets lingered, waiting for tools precise enough to prove it true. In 1995, that proof arrived. Two astronomers, Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in France, announced they had detected a planet orbiting a star called 51 Pegasi. It wasn't visible, but its presence was unmistakable. The star's light shifted back and forth in a steady rhythm, exactly what would happen if a large planet were pulling on it. The planet 51 Pegasi b was the first confirmed exoplanet orbiting a sun-like star. It was a giant, roughly half the mass of Jupiter, orbiting extremely close to its star, so close that its year lasted only about 4 Earth days. The discovery was shocking. No one expected a massive planet to orbit so near its star. In our own solar system, the large gas giants live far out beyond the asteroid belt. A planet like Jupiter wasn't supposed to exist in an orbit tighter than Mercury's. But there it was, defying expectations and rewriting the rules. Astronomers had to rethink their theories of how solar systems form. Maybe nature was more inventive than we'd imagined. That single discovery changed everything. If one star could have a planet, so could others. And if planets could form in unexpected places, perhaps they were far more common than we thought. Within a few years, more exoplanets were found using the same technique, measuring the tiny shifts in starlight caused by orbiting companions. The number began to grow, slowly at first, then rapidly as instruments improved. Each new detection confirmed what had once been only a dream. The galaxy was full of worlds. As the evidence accumulated, the variety of planets stunned everyone. Some were giants that circled their stars in a matter of days, others were smaller and more distant. A few followed eccentric orbits, swinging close and then far away. The systems didn't look much like ours. Many had configurations that seemed chaotic or unstable, but the more we learned, the more we realized that our solar system might not be typical. There was no single blueprint. Planetary systems came in all shapes and sizes. The next big step came with a spacecraft designed specifically to look for planets. NASA's Kepler telescope. Launched in 2009, it was a quiet observer, staring at a single patch of sky in the constellation Cygnus. Its mission was simple but ambitious, to watch thousands of stars continuously and look for small, periodic dips in brightness. Those dips could mean that a planet had crossed in front of the star, briefly blocking a tiny fraction of its light. The effect was minute, less than a 1% dimming, but Kepler was sensitive enough to see it. For 4 years, Kepler stared without blinking, recording light curves from more than 150,000 stars. What it found changed our understanding of the galaxy forever. Thousands of planets revealed themselves through those tiny dips in brightness. Some were giant and hot, others small and rocky. Some orbited close, some far. There were planets in multiple star systems, planets with odd tilts, planets locked in resonant orbits that danced in gravitational harmony. The data was overwhelming. Suddenly we weren't asking whether other solar systems existed. We were asking how many there were, and how different they might be from our own. Kepler's discoveries showed that planets are not rare exceptions. They're practically guaranteed. Statistically, there are more planets than stars in the Milky Way. That means hundreds of billions of solar systems, each unique, each with its own architecture. Some may have just 1 or 2 planets, others may have 10 or more. Many may have moons, rings, comets, and asteroid belts. The diversity of planetary systems seems endless, shaped by subtle variations in physics, chemistry, and chance. Even with all this knowledge, we're still at the beginning. The planets we found are mostly the ones that are easiest to detect. Large ones close to their stars. Smaller, Earth-sized planets are harder to see, their signals fainter, their shadows smaller. Yet even among these faint traces, we found hundreds of worlds roughly similar in size to our own. Some lie within their star's habitable zone, where temperatures might allow liquid water to exist. Others orbit red dwarfs, stars smaller and cooler than the Sun but far more numerous. Statistically, that means there could be billions of potentially habitable planets in our galaxy alone. When astronomers say habitable, they don't necessarily mean comfortable. They mean simply that the basic conditions for liquid water might exist. Not too hot, not too cold. Life as we know it depends on water, but life as we don't know it might depend on other things. The universe doesn't limit itself to our preferences. What's exciting is the possibility itself. For the first time in history, we can look at the sky and know that many of those stars almost certainly have planets, where chemistry and chance might have combined to create something alive. As new instruments come online, we're learning more about what these distant worlds are actually like. Some telescopes can analyze the light that passes through an exoplanet's atmosphere during a transit. That light carries clues about what gases are present: hydrogen, methane, carbon dioxide, even water vapor. Each molecule leaves a distinct pattern, a spectral signature that can be measured. With enough precision, we can infer whether a planet's air might be breathable, toxic, or something entirely alien. It's not easy. The signals are faint, the data fragile, but every new spectrum adds a piece to the puzzle. Other methods have emerged too. Some astronomers use direct imaging, blocking the star's light to reveal the faint glow of its planets. It's like trying to spot a firefly beside a lighthouse from miles away. Yet even that impossible-sounding feat has been achieved for a handful of systems. Others use gravitational microlensing, watching how a star's light bends when another object passes in front of it, briefly magnifying it. Sometimes that object is a planet. Each method adds another way of seeing what was once invisible. The discovery of other worlds isn't just a triumph of technology, it's a shift in perspective. For centuries, humans placed themselves at the center of creation. Then we learned that Earth orbits the Sun. Then that the Sun is one star among billions in the Milky Way. Now we know that almost every one of those stars likely has its own planets. The universe didn't stop at one example. It repeated the pattern billions of times. We're not the exception. We're the evidence of a universal rule. When you think about that, the scale becomes almost dizzying. Every patch of night sky holds thousands of potential solar systems. The star you notice just above the horizon, the one you can barely see, could have its own planets circling it right now, each with its own seasons and climates. Some might have atmospheres thick with clouds. Others might be bare and silent, their surfaces frozen or molten. All of them are part of the same galaxy, moving together through space, orbiting the center of the Milky Way in vast, slow spirals that take hundreds of millions of years to complete. To look at the night sky now is to see it differently. Once, those lights were symbols of eternity. Now we know they're living systems, each one changing over time. Stars are born, age, and die, and their planets change with them. When a star expands into a red giant, its inner planets may be consumed, while outer ones freeze in darkness as the star collapses into a white dwarf. Some planets may survive the death of their stars. Others may be flung out entirely, wandering the galaxy alone. Every star's family has its own fate written in gravity and time, and yet, for all the drama, the view from Earth is peaceful. We see only the calm surface, the distant twinkle of light, the violence of creation, the slow collapse of stars, the birth of new worlds all happen in silence. Even the most turbulent systems are too far away to disturb us. That distance gives the universe its serenity. It's why the stars can be both dynamic and soothing, both ancient and ever-changing. When you step outside at night, you're looking at a cosmic landscape billions of years in the making. The light you see left those stars long before human civilization began. Some of the stars you see may already be gone, their light still travelling through space, a lingering echo of their existence. Others may be young, just beginning to shine. Somewhere among them are systems that mirror ours, with rocky planets orbiting in warmth, maybe with oceans, maybe with atmospheres that shimmer in twilight. You can't see them with your eyes, but they're there, part of the grand pattern that connects everything. It's easy to feel small in all this, but small doesn't mean insignificant. The same processes that shape those distant systems shaped us too. The atoms in your body were forged in the cores of ancient stars, carried into space by explosions, gathered into the cloud that became our solar system, and eventually into the Earth itself. When you breathe, you're recycling material that once belonged to suns long gone. In a very real sense, you are part of the Milky Way story. You're made of the same matter that fills the space between stars. Every discovery of another world is also a discovery about ourselves. It shows us that the conditions that gave rise to Earth are not rare. They happen again and again, wherever there's light and dust and time. The galaxy is not empty. It's alive with motion, colour and possibility. From Earth's sky, we've gone to other worlds without leaving home, simply by learning to read the faintest signals of light. The universe speaks quietly, but it never stops speaking. And now, as telescopes continue to scan the heavens, we're preparing to take the next step. Not just finding planets, but studying them as places, understanding their atmospheres, their weather, their seasons, their chemistry. Soon, we may know what colours their skies are, what their days and nights look like, how their suns set. We may even find the faint signs of biology, patterns in light that can only come from living processes. That possibility is what drives the search forward. Somewhere out there, among the countless solar systems in our galaxy, might be a world that has its own watchers, its own nights, its own quiet thoughts under a familiar sky. The journey from Earth's sky to other worlds has already begun, and it hasn't required us to leave orbit. All it's taken is patience, precision, and the simple act of paying attention to the universe. From the faintest wobble of a star to the briefest flicker of light, we've learned to read the galaxy's language. Every signal, every discovery, is a reminder that the stars above are not just distant lights. They are homes. They are suns with stories, and we are finally learning how to listen. When the idea of planets beyond our sun began to shift from speculation to evidence, it didn't happen with the kind of triumph you might imagine. There was no single night when astronomers looked through a telescope and suddenly saw a tiny new world gleaming beside a distant star. The truth arrived quietly, buried in data, teased out by patient observation and long skepticism. The first confirmed exoplanets were not found around stars like our sun, but around something stranger, colder, and far less welcoming. They were discovered circling the remnants of a dead star, a pulsar, and their existence changed astronomy forever. A pulsar is the collapsed core of a massive star that exploded as a supernova. What remains is a neutron star, a sphere barely 20 kilometers wide but heavier than the Sun. It spins rapidly, sending out beams of radiation like a cosmic lighthouse. As it rotates, those beams sweep across space in regular pulses. To an astronomer with the right instruments, the pulsar's rhythm is precise, more accurate than any clock. That precision is what makes it such a good place to notice anomalies. If the timing of those pulses shifts, even slightly, it means something is tugging on the neutron star, altering its motion in space. In 1992, a pair of astronomers named Alexander Wolszczan and Dale Frail were studying one such pulsar known as PSR B.712. It lay about 2,000 light-years from Earth, spinning 30 times a second. Its pulses arrived with perfect regularity, almost perfect. Wolszczan noticed tiny irregularities in the timing. At first he assumed it was noise, some glitch in the instruments or interference from the telescope. But as he analysed the data more carefully, a pattern emerged. The timing variations weren't random. They repeated in cycles, suggesting that something massive was orbiting the pulsar and tugging it back and forth ever so slightly. When the calculations were done, the result was astonishing. The irregularities could only be explained by planets, not one, but two, both roughly the size of Earth, orbiting the pulsar. Later, a third, smaller planet was found. These were the first confirmed exoplanets, worlds beyond our solar system, orbiting a star that had already died. It was a strange place to find them. Pulsars are hostile environments, blasting out radiation that would destroy any known form of life. Yet somehow these planets existed. They might have been survivors from before the supernova, or they might have formed afterward from the debris left behind. Either way, their discovery proved that planets could exist under conditions no one had expected. The reaction in the scientific community was cautious at first. After decades of false alarms and overeager claims, astronomers had learned to be skeptical. Many wanted independent confirmation, and for good reason. Earlier in the 20th century, several astronomers had claimed to see evidence of planets around nearby stars, but none of those claims held up to scrutiny. This time, however, the data was clear. The pulsar's rhythm was too regular to be mistaken, and the timing variations fit perfectly with the gravitational pull of orbiting planets. The discovery was solid. For the first time, humanity knew, not guessed, not hoped, but knew that planets existed beyond our own solar system. The news didn't make front-page headlines. The general public didn't yet understand the significance, and the setting, a dead star 2,000 light-years away, lacked the romance of habitable worlds or alien landscapes. But among astronomers, it was a revolution. The universe had just opened another door. Planets weren't confined to stars like the Sun. They could form or survive even in the aftermath of stellar death. If planets could exist there, they could exist almost anywhere. The search that followed would expand faster than anyone could have predicted. Just 3 years later, in 1995, Michel Mayor and Didier Queloz announced another discovery, this time around a living sun-like star. The star was 51 Pegasi, located about 50 light-years away in the constellation Pegasus. The planet, later named 51 Pegasi b, was enormous, roughly half the mass of Jupiter, and it orbited its star in just 4 days. Its proximity meant it was extremely hot, with surface temperatures that could melt metal. It was nicknamed a hot Jupiter, and it defied everything scientists thought they knew about planetary systems. In our solar system, large gas giants stay far from the sun, but here was a giant world practically hugging its star. Either our solar system was unusual, or our understanding of planet formation was incomplete. Mayor and Queloz had used a technique known as radial velocity, measuring the subtle shifts in the star's light as the planet's gravity pulled it back and forth. It wasn't an easy detection. The movement was just a few dozen meters per second, barely noticeable in the star's spectrum, but it was enough. The signal was clean, consistent, and unmistakable. Once again, astronomers checked, double-checked, and debated, and once again, the evidence held. The planet was real. This second discovery changed the tone of the entire field. The pulsar planets had been strange and isolated. This one felt closer to home. A normal star. A confirmed planet. A method that could be applied to many more targets. Suddenly, the hunt for exoplanets became a global effort. Observatories around the world joined in, refining instruments, watching hundreds of stars at once. Within a few years, dozens of new planets were found using the same method. Each discovery was another reminder that the universe was far more complex and creative than our limited models had allowed. The early exoplanet catalogue grew rapidly, and with it, our sense of wonder. There were massive planets orbiting so close to their stars that their atmospheres were being blown away. Others travelled on elongated orbits, diving near their stars and then swinging far out into the cold. Some systems had multiple giants packed into tight spaces, locked in gravitational resonance. Each new find challenged assumptions. It became clear that our solar system, with its wide spacing and gentle orbits, was just one of countless variations. Detecting exoplanets in those early years was a challenge of patience and precision. Instruments had to measure changes in light smaller than a fraction of a percent. Every piece of data had to be checked for errors caused by the telescope, the atmosphere, or the instruments themselves. Astronomers spent long nights staring at graphs and spectra, looking for the faint, regular patterns that betrayed a planet's presence. The reward for that patience was extraordinary. Each confirmation was the discovery of another world. It's worth remembering how radical this was. For most of human history, the existence of other planets had been a question for philosophers, not scientists. When Giordano Bruno suggested in the 16th century that every star might be a sun with its own worlds, he was mocked and ultimately executed for heresy. In the centuries that followed, thinkers like Fontenelle and Kant speculated about inhabited worlds, but no one could prove it. The night sky was vast, but it offered no evidence. Only in the late 20th century, with sensitive instruments and powerful computers, did the question finally move from philosophy to observation. The first exoplanets didn't fit neatly into expectations of habitability or comfort. They were often extreme: scorched gas giants, frozen giants, or worlds circling pulsars. But their diversity hinted at something deeper. If planets could exist in such harsh conditions, then they could also exist in calmer ones. If the galaxy could produce planets by the thousands, then surely some must be small, rocky, and temperate like Earth. The question was no longer whether planets were out there, but what kinds they were, and how many might resemble home. The discovery of the first exoplanets triggered a wave of new technology. Astronomers developed more sensitive spectrographs, capable of detecting velocity changes of just a few meters per second. Space agencies began planning dedicated missions to search for transits, the tiny dips in brightness caused when a planet passes in front of its star. It was the beginning of a new era, one where astronomy turned from studying stars themselves to studying the worlds that orbit them. By the early 2000s, the catalogue of known exoplanets had grown into the hundreds. Many of them were hot Jupiters, easy to detect because of their size and proximity to their stars. But as instruments improved, smaller planets began to appear. Neptune-sized, then super-Earths, and finally, Earth-sized. The distribution of planets began to reveal patterns. Some systems were compact, with multiple worlds packed tightly together. Others were wide and sparse. Some orbits were tilted or even retrograde, moving opposite the direction of their star's rotation. Nature, it seemed, was not limited to our imagination. Each new discovery added context to our understanding of the galaxy. The Milky Way, once thought to be a collection of solitary stars, was now understood as a vast network of planetary systems. Every point of light in the sky likely had companions, planets, moons, rings and debris swirling in their own gravitational harmony. The realization carried a quiet, almost meditative significance. The universe had always been populated, we just hadn't seen it. What made these discoveries even more powerful was their universality. The same physical laws that governed our solar system governed all of them. The same equations of gravity, the same principles of motion, the same chemistry of dust and gas. From pulsar planets to hot Jupiters, every world was a variation on the same cosmic recipe. The diversity didn't reflect chaos, it reflected the creativity of physics itself. Even so, the early years of exoplanet research were filled with surprises. Some planets orbited so close to their stars that they completed a revolution in less than a day. Others orbited two stars at once, like the fictional Tatooine, experiencing double dawns and double sunsets. There were planets with densities so high they were likely made of solid metal, and others so low they could float in water. Each system was a small experiment in the possibilities of matter and motion. As more data came in, astronomers began to see broader trends. Planet formation, once thought to be rare, turned out to be almost inevitable. Wherever stars formed, disks of gas and dust surrounded them, and within those disks, gravity sculpted planets. Sometimes they formed in stable, orderly systems. Other times, their interactions sent them scattering into interstellar space. The galaxy, it turned out, was full not just of stars, but of worlds, and not just bound ones, but wandering ones too, rogue planets drifting alone between the stars, torn from their homes by gravity's unpredictable pull. The story of the first exoplanets is the story of humility in science. Each discovery forced us to let go of assumptions, to accept that nature doesn't conform to human expectations. When we imagined other worlds, we thought they would look like ours, orderly, balanced, familiar. Instead, we found extremes. But those extremes were part of the same process that made Earth. The universe doesn't play favourites. It creates endlessly in every form it can. What began with the flicker of a pulsar and the wobble of a star has grown into an entire field of study. Today, thousands of exoplanets are catalogued, and tens of thousands more await confirmation. Future missions are planned to study them in detail, to image them directly, and to search their atmospheres for signs of life. The discoveries that began with faint irregularities in data now define one of the most exciting frontiers in modern astronomy. If you step outside and look up at the sky tonight, the stars you see are not isolated points. Each one could have its own set of planets, some large, some small, some warm, some frozen. The first exoplanets we found were strange and inhospitable, but they were proof that the universe builds worlds wherever it can, and if it builds them everywhere, then somewhere, perhaps not far, perhaps unimaginably far, there may be others like ours, planets where light falls softly on oceans, where clouds gather and break, where something looks up at the same stars and wonders what else is out there. The story continues, but that first step, that first confirmation, remains one of the most profound in human history. It took us from isolation to belonging, from thinking of Earth as unique to seeing it as part of a vast galactic family. The first exoplanets were the beginning of a new way of understanding the night sky, not as a dome of light, but as a landscape of worlds. And though the discoveries have multiplied, the feeling remains the same: quiet awe, deep curiosity, and the calm realization that every star may carry its own story, waiting for us to listen closely enough to hear it. By the time the first exoplanets had been confirmed, astronomy stood on the edge of a new kind of exploration. We had found proof that planets existed beyond the Sun, but we were still seeing only the biggest, brightest, easiest ones to detect. The ones that tugged hard on their stars or that burned so close to them that their presence was impossible to miss. The smaller, quieter planets, the ones like Earth, remained hidden. We knew they must exist. The physics of star formation made that almost certain. But knowing something should be true and being able to see it are very different things. That was the gap the Kepler telescope was built to close. The Kepler mission was simple in concept and profound in consequence. It was a telescope that didn't look across the whole sky, but stared instead at a single, unremarkable patch of it. For years, it would fix its gaze on one small area in the constellations of Cygnus and Lyra, a window holding about 1/400th of the sky. That might sound small, but within that patch were over 150,000 stars. The idea was that if any of those stars had planets passing in front of them, the planets would cause tiny, regular dips in brightness, brief faint eclipses repeated with clockwork precision as the planets orbited their stars. It was a method called the transit technique, and it demanded extraordinary patience and precision. The dimming caused by an Earth-sized planet crossing a Sun-like star is less than 1 part in 10,000. To detect it, the telescope had to remain still, stable and unblinking for years. Kepler was designed to do exactly that. Launched in March of 2009, it drifted into an Earth-trailing orbit around the Sun, slowly falling behind our planet as it began its long watch. It didn't turn or scan, it simply stared, recording the light from thousands of stars at once, measuring their brightness with exquisite care. The mission wasn't about finding 1 or 2 planets. It was about statistics. It was designed to answer a simple but fundamental question: how common are planets in our galaxy? If you look at enough stars, how many of them show signs of orbiting worlds? Kepler's field of view was a small sample, but if you could count planets there, you could infer how many must exist across the entire Milky Way. It was, in a way, a cosmic census. At first, Kepler's data looked like noise. Stars flicker naturally, their surfaces boiling with convection and magnetic storms. Even without planets, their brightness varies. But as astronomers processed the data, patterns emerged. Tiny, repeating dips, too regular to be random. Each one represented a possible planet. A single dip wasn't enough. Stars can dim for many reasons. But when the same pattern repeated, precisely timed, it revealed an orbit. The more dips, the more certain the planet. Within the first few months, Kepler had identified hundreds of candidates. Within a year, thousands. Each signal needed verification. Each potential planet needed to be checked for false positives. But the scale of discovery was breathtaking. There were planets everywhere. Big ones, small ones, fast ones, slow ones. Some orbited close enough that their years lasted only days. Others circled far away, completing a revolution in years. Kepler had turned a patch of sky into a living laboratory, and what it found was abundance. For the first time, we could see the distribution of planetary sizes and distances on a galactic scale. There were countless small rocky worlds, many just slightly larger than Earth. There were gas giants like Jupiter, but they were outnumbered by what astronomers called super-Earths, planets between Earth and Neptune in size, worlds that didn't exist in our own solar system, but seemed to be everywhere else. That discovery alone changed our understanding of what was typical in the galaxy. The universe, it seemed, was better at making medium-sized planets than we were. The beauty of Kepler's method was its simplicity. It didn't rely on massive gravitational wobbles or direct imaging. It just watched light. The idea that you could learn so much from such tiny variations in brightness is quietly poetic. Light, after all, is the only messenger we have from most of the universe. Every bit of information we gather about stars, galaxies, or planets arrives as light. Kepler turned that fragile signal into a map of hidden worlds. As the data poured in, it became clear that planets were not the exception, but the rule. Nearly every star observed seemed capable of hosting them. Some had multiple planets, forming miniature solar systems with regular repeating transits. A few had up to 6 or 7 planets, orbiting in tight harmony, their periods locked in gravitational resonance. These systems defied imagination. Planets packed so close together that their skies would be filled with one another, each one glowing like a moon in the other's heavens. For astronomers who had spent their careers searching for even a single world beyond the Sun, Kepler's results were overwhelming. The catalogue of confirmed planets grew from a few dozen to hundreds, then thousands. Each one was unique. There were lava worlds, ice worlds, ocean worlds, planets tidally locked so that one side was in perpetual day while the other froze in endless night. There were planets around binary stars, orbiting both suns in wide, stable loops. There were worlds orbiting small red dwarfs, their stars dim but steady, their habitable zones close enough that a planet could circle them in weeks and still have temperate conditions. Among all these discoveries, some stood out for their familiarity. In 2011, Kepler identified a planet called Kepler 22b, about 600 light-years away. It was roughly twice the size of Earth, and lay within its star's habitable zone, the region where temperatures could allow liquid water. It wasn't Earth's twin, but it was the first solid evidence that potentially habitable worlds existed elsewhere. Others soon followed: Kepler 62f, Kepler 186f, Kepler 452b. Each of them small, rocky, and orbiting at just the right distance from their stars. For the first time, we had real examples of worlds that could, in theory, resemble our own. It's hard to overstate how transformative this was. For centuries, humanity had wondered whether there were other Earths. Philosophers debated it, poets dreamed of it, scientists hypothesized it. Now, the question had an answer. Yes, there are other Earth-like planets. They're not rare or unique, they're common. Our world is one among billions. The night sky, once thought to hold distant, lifeless stars, now seemed to shimmer with possibility. Kepler's discoveries didn't just expand our sense of number, they also deepened our understanding of planetary formation. Before Kepler, models of how solar systems formed were based almost entirely on ours. We assumed planets formed from a disk of gas and dust, settled into stable orbits, and remained there. But Kepler showed that planetary systems are far more dynamic. Planets migrate inward or outward. They interact gravitationally, sometimes swapping places or colliding. Their orbits can shift dramatically over time. Some systems stabilize into neat arrangements, others remain chaotic. The diversity revealed by Kepler forced astronomers to rewrite almost every theory of how planets form and evolve. Not everything about the mission went smoothly. Space exploration rarely does. In 2013, after 4 years of near-continuous observation, Kepler suffered a failure in 2 of its 4 reaction wheels, the gyroscopes that kept it stable. Without them, it could no longer maintain its steady gaze. For a time, it seemed the mission was over. But engineers found a clever solution. By using sunlight as a stabilizing force and carefully balancing the spacecraft, they were able to continue operations under a new mission called K2. Instead of staring at one patch of sky, Kepler now observed a series of different fields, each for about 80 days. It continued to find planets until 2018, when its fuel finally ran out. By then, it had revolutionized our understanding of the galaxy. Over its 9 years of operation, Kepler discovered more than 2,600 confirmed planets and identified thousands of additional candidates. But its impact can't be measured in numbers alone. It changed the way we think about our place in the universe. Before Kepler, we didn't know how common planets were. After Kepler, we understood that they are nearly everywhere. The Milky Way is a galaxy of solar systems. Every star you see in the night sky, and countless you don't, likely has planets orbiting it. That realization is one of the most profound shifts in human perspective since we learned that the Earth orbits the Sun. The data from Kepler is still being analysed. Astronomers continue to mine its archives, discovering new planets years after the telescope stopped observing. The precision of its measurements allows scientists to study not just the planets themselves, but the stars they orbit. Kepler's observations have provided insights into stellar oscillations, binary systems, and the life cycles of stars. In that sense, it's still teaching us, still sending its quiet message across time, a message written in light. What makes the Kepler story so moving is its humility. The telescope didn't travel to other worlds. It didn't send back pictures or landscapes. It simply watched. For years, it stared at a tiny patch of sky and waited for faint shadows to repeat. From that stillness, from that patience, came a transformation in our understanding of the cosmos. There's something deeply human in that approach, the willingness to wait, to observe carefully, to trust that the universe reveals itself slowly. Even now, as new telescopes take Kepler's place, the Transiting Exoplanet Survey Satellite, the James Webb Space Telescope, the upcoming Plato mission, they all build on the foundation Kepler laid. Its data is the baseline, its methods the template. Every exoplanet discovered today is part of the same lineage of light, tracing back to that quiet spacecraft drifting in its orbit, patiently watching the stars flicker. When you think about what Kepler did, the scale becomes almost dizzying. From a small telescope staring at a single slice of sky, we learned that the Milky Way alone likely holds more planets than there are grains of sand on all the beaches of Earth. Each one is a world, orbiting a star, following the same fundamental laws that govern us. Some are inhospitable, some are perhaps serene, some are still forming, and some are already gone. The galaxy is a living system, and Kepler showed us that its lifeblood is planetary. It's easy to forget that all of this, all these discoveries, came not from seeing worlds directly, but from seeing their absence of light, from shadows, from the faintest dips in brightness. Kepler's genius was in understanding that you don't always need to see something to know it's there. You just need to measure carefully enough to notice the patterns hidden in the quiet. That idea resonates beyond astronomy. It's a reminder that the universe is full of signals, if only we slow down enough to notice them. The Kepler mission changed not just science, but imagination. It gave us numbers to match our wonder. It told us that Earth-like planets are common, that solar systems are the norm, that the night sky is not a scatter of random lights, but a map of possible homes. For anyone who looks up at night and wonders what else might be out there, that knowledge is both humbling and comforting. We are part of a vast network of suns and worlds, a galaxy alive with possibility. And so the Kepler telescope, though long silent, continues to influence how we see the universe. Its legacy isn't just the planets it found, but the realization it left behind, that the cosmos is richer, more populated, and more connected than we ever dared to believe. Somewhere out there, among the billions of stars, countless other worlds move in quiet orbits, unseen but certain, each one a faint flicker waiting for its own moment of discovery. When you look up tonight, try to imagine that patch of sky Kepler watched for so many years. To the naked eye, it looks empty, just a faint scatter of stars in the darkness. But hidden there are thousands of worlds, circling, spinning, moving through their own days and nights. Kepler revealed what was always there, not by changing the universe, but by teaching us how to see it. When scientists first began to count the stars, they knew it was an impossible task. Even with the naked eye, the sky offered more lights than anyone could truly tally, and beyond those visible points lay countless more. Yet humans have always been drawn to counting, to naming, to trying to bring the infinite into the language of numbers. It's one of the ways we understand the world, by measuring it, by finding patterns, by estimating what lies beyond what we can see. When it comes to the Milky Way and its solar systems, counting becomes both a science and a kind of meditation. We know the numbers can never be exact, but still we try. The first step in that great cosmic census is understanding what we're counting. A solar system is a star, and all the material bound to it by gravity. Planets, moons, asteroids, comets, dust, and gas. By that definition, every star could, in theory, have its own solar system. The Milky Way contains hundreds of billions of stars, perhaps more. If even a fraction of them host planets, then the number of solar systems would also be in the hundreds of billions. But counting them isn't as simple as multiplying one by another. It means asking how planets form, how many survive, and what kinds of systems exist in the first place. The discoveries from Kepler and other telescopes gave astronomers the first solid basis for estimation. Kepler observed a small region of the sky, about 1/400th of the total area, and within that field it found thousands of planets. By applying those statistics to the rest of the galaxy, scientists could infer the broader picture. Roughly speaking, there are more planets than stars. On average, every star has at least one, and many have multiple. That means there could be over 400 billion planets in the Milky Way alone, perhaps even more. Of course, most of these worlds will never be seen. They're too distant, too dim, or too close to their stars. Many don't align in a way that allows us to detect them through transits, and their gravitational effects are too subtle to measure. For every planet discovered, there are thousands more hidden. But astronomy doesn't rely on direct sight alone. It relies on probability and modelling. By understanding how often planets appear around certain types of stars, scientists can make educated estimates. What emerges from those calculations is staggering. The galaxy isn't just sprinkled with planets, it's saturated with them. To understand what those numbers mean, it helps to imagine the structure of the Milky Way. It's a disk about 100,000 light-years across, containing spiral arms rich with gas and dust. Most of the stars, and therefore most of the planets, lie within these arms, orbiting the galactic centre like beads on vast invisible threads. If you could somehow look at the galaxy from above, you'd see billions of suns embedded in those glowing streams, each one surrounded by its own unseen companions. The scale defies intuition. Even the smallest regions of space that appear empty are filled with countless systems, separated by light years but bound together by the same gravitational architecture. When astronomers describe the Milky Way as having hundreds of billions of solar systems, it's not a poetic exaggeration. It's the best estimate based on data, refined with every new observation. The current understanding is that nearly every star, at least 9 out of 10, has one or more planets. That means solar systems are not special arrangements, they are the natural outcome of star formation. Whenever a star is born from a cloud of gas, the leftover material flattens into a rotating disk. Within that disk, dust particles stick together, forming larger clumps. Over millions of years, those clumps grow into planets. It's not an exception. It's the rule. Nature doesn't make lone stars, it makes families. That realization changed the way we think about the cosmos. For a long time, humans imagined themselves living under a unique configuration of celestial order. One sun, a few planets, and a blue world that somehow supported life. But once we learned that nearly every star might have planets, our sense of isolation dissolved. The galaxy became a community of systems, each with its own story. Counting them became less about precision and more about perspective, an exercise in understanding scale. The number is too large to visualize, so we approach it through analogy. Imagine holding a handful of sand from a beach. Each grain represents a star. The handful might hold thousands, but the entire beach would hold billions. Now imagine that almost every grain of sand has at least one tiny companion clinging to it. A planet. Invisible, but present. That's the Milky Way. And if you added up all the galaxies in the observable universe, each with its own billions of stars and planets, the numbers quickly exceed comprehension. There are more worlds in the universe than grains of sand on every beach on Earth. It's not a metaphor. It's a literal comparison supported by astronomical data. When astronomers make these estimates, they use careful statistical models. They start with the stars that Kepler observed, mostly those similar to our Sun, and calculate the fraction that showed planets. Then they correct for detection biases. Kepler could only see planets that passed directly in front of their stars from our point of view, so it missed many others. By adjusting for that geometry, scientists can infer how many planets likely exist overall. They also consider different types of stars: massive ones, small red dwarfs, binary systems. Each type has its own likelihood of hosting planets. Red dwarfs, which make up the majority of stars, tend to have smaller, closer planets. Hot, massive stars may have fewer, or their planets may not survive long in their strong radiation fields. When all these factors are combined, the estimates converge on a remarkable conclusion. The galaxy is full of solar systems. Still, there's a difference between counting and knowing. We can say that there are likely hundreds of billions of solar systems, but that number remains an approximation, a reflection of what we've seen so far. There are regions of the galaxy we can barely observe, obscured by dust, hidden behind dense molecular clouds, or simply too distant. In those regions, the same processes are unfolding, stars being born, disks forming, planets coalescing. The galaxy is dynamic, and our senses can only ever capture a moment in its vast ongoing evolution. Some parts of the Milky Way are more fertile than others. In the spiral arms, where gas and dust are plentiful, star formation is active, and new planetary systems form regularly. In the central bulge, where stars are older and closer together, many systems may have already aged past stability, their planets burned away or consumed. In the outer halo, where material is sparse, fewer new systems emerge, but even the quiet regions are not empty. Gravity has a way of recycling matter. When stars die, they return their material to space, enriching it with heavier elements that make planet formation easier the next time around. The galaxy is a vast ecosystem, constantly regenerating itself, building new systems from the ashes of old ones. The act of estimating such a number might seem dry, but it carries an almost spiritual weight. It tells us that our solar system is not an accident. It's one example among billions shaped by the same universal forces. When we say there are 100 billion solar systems in our galaxy, what we're really saying is that the universe is prolific, that creation is continuous. Every star that ignites is an opportunity for worlds to form, for moons to orbit, for light to fall on alien surfaces we can only imagine. The sheer abundance is both comforting and humbling. Counting the uncountable requires accepting uncertainty. Even within our own solar system, there are mysteries we haven't resolved. Objects at the edge we can't see, comets from the Oort cloud that may never return. Scale that up to the galactic level, and the complexity becomes infinite. We can estimate averages and probabilities, but the details remain hidden. Some solar systems may have dozens of planets, others may have only one. Some may have moons larger than Mercury, others may have none at all. The diversity is beyond cataloguing. And yet, despite that uncertainty, our models grow more precise. With each new mission, Kepler, TESS, Gaia, JWST, we refine our understanding. TESS, the Transiting Exoplanet Survey satellite, now surveys almost the entire sky, building on Kepler's legacy. It's finding planets closer to Earth, around brighter stars, systems we can study in more detail. Gaia, meanwhile, is mapping the positions and motions of over 1 billion stars, helping us understand how they move and cluster. Combined, these missions are transforming our rough estimates into detailed maps of the galaxy's planetary population. Even so, the true number of solar systems will likely never be known. The universe is too large, and our perspective too narrow. But perhaps that's the beauty of it. The goal isn't to finish counting, but to keep exploring, to keep expanding the boundary of what we can perceive. Each discovery, each new solar system added to the list, is a reminder of how much remains unseen. The act of counting becomes an act of curiosity, not completion. If you could travel across the galaxy, system by system, you'd never finish. You could spend a lifetime visiting one world per second, and still barely make a dent. Each star you passed would bring new configurations, planets large and small, some glowing with heat, others drifting through cold shadows. Some systems would have double suns, some would orbit quiet red dwarfs that have burned for trillions of years. Every stop would reveal a new version of the same cosmic experiment. What happens when gravity, time, and matter play together long enough? Astronomers often talk about numbers in terms that sound abstract, hundreds of billions, trillions, quadrillions, but behind each number is something real, something physical. When we say there are perhaps 400 billion solar systems in the Milky Way, we're not just speaking about points of light. We're talking about worlds. We're talking about landscapes that exist right now under alien skies. Mountains, oceans, storms, ice, clouds, winds, perhaps even organisms, all invisible, all real. The number becomes more than a statistic. It becomes a measure of possibility. There's another layer to this counting, the recognition that we're part of it. The Earth isn't separate from the systems we count. It's one of them. Our Sun is one star among billions. Our planet's part of the same grand equation. When we count the stars and the systems they hold, we're also counting ourselves. We're not outside observers tallying the universe from afar. We're participants, existing within one of its countless families. As we continue to measure, to estimate, and to map, we come closer to understanding not just how many solar systems there are, but how they're distributed, how they evolve, and what makes them stable. Some systems may last for billions of years, others may be temporary, disrupted by passing stars or collisions. Some planets may drift away into interstellar space, turning into rogues. The galaxy is dynamic, its numbers shifting constantly, even as we try to freeze them into understanding. Counting the uncountable isn't about reaching the end of the list. It's about realizing that the list has no end. The Milky Way isn't a static collection of stars, it's a living process. Stars are born, planets form, systems die, and new ones replace them. The numbers change, but the rhythm stays the same. Somewhere in the galaxy, right now, a new star is igniting, and around it dust is beginning to swirl. The first grains of a new solar system are clumping together, beginning their slow journey toward becoming planets. If you could wait a few million years, you'd see those planets form, their orbits settle, their skies clear. And in that same moment elsewhere, another system is fading away, its star exhausted, its planets adrift. The galaxy breathes in systems and exhales them again. When scientists speak of hundreds of billions of solar systems, they're not counting static objects, they're counting moments in time. Each number is a snapshot of a living galaxy, changing and self-renewing. The uncountable isn't just the quantity, it's the motion, the change, the unending flow of creation and decay. We count what we can, but we also accept that most of it will always remain beyond our reach. And perhaps that's the most peaceful truth of all. The sky above isn't empty, and it isn't still. It's alive with more systems than we could ever number, each one turning quietly in its orbit, each one part of the same cosmic story. Counting them doesn't end with a total. It ends with an understanding that we live in a galaxy where creation never stops, where there's always another system forming somewhere, always another world waiting to be seen. When you look at a diagram of our solar system, it always seems so neat. The planets arranged in gentle circles, each orbit a tidy ring around the sun, each world following its path like a bead on a string. It gives the impression of order, of precision, of balance. For centuries we imagined that this was how every solar system must look: organized, symmetrical, predictable. It felt right that the universe would repeat that pattern. But as soon as we began to discover other systems, that assumption began to dissolve. The reality turned out to be far stranger, more varied, more creative than we ever expected. Other solar systems don't necessarily resemble ours. Some are compact and crowded, with planets packed so tightly that their orbits nearly touch. Others are sprawling, with worlds separated by distances so vast that communication between them would take centuries. Some orbit a single star, others 2 or even 3. Some follow nearly circular paths, others are stretched into ellipses so elongated that they spend most of their time in darkness, before rushing close to their stars for a brief searing summer. The diversity of these arrangements tells us something profound, that the universe doesn't build systems according to one blueprint. It builds them in every way it can. When scientists first started finding exoplanets, they expected to see copies of our own structure: small, rocky planets close to the star, large gas giants farther out, circular orbits, stable spacing. That's what the early models of planet formation predicted. But the first discoveries upended those expectations immediately. The giant planets that Kepler and earlier telescopes found were often orbiting incredibly close to their stars. Some circled in just a few days. They were enormous, hot and heavy, the so-called hot Jupiters. According to the old rules, they shouldn't have been there. The gas that forms such massive planets shouldn't exist that close to a star's heat. The only way to explain it was to imagine that these planets had formed farther away and then migrated inward, pulled by complex gravitational interactions with the disk of gas and dust that surrounded their young stars. That idea, planetary migration, changed everything. It meant that solar systems could evolve dramatically after formation. Planets might not stay where they began. They could move inward or outward, collide, swap orbits, or even be ejected entirely. Systems that looked stable at first could become chaotic over time. The arrangement of planets around a star wasn't a permanent structure, but a dynamic, shifting landscape. It was a realization that turned solar systems from static diagrams into living, changing systems. If you could see some of these other systems up close, they would look nothing like the models we grew up with. Some would seem familiar at first glance, but others would defy intuition. There are planets that orbit 2 stars, like a cosmic dance where the suns circle each other while the planet moves around them both. From the surface of such a world, if you could stand there, you'd see 2 suns rising and setting, sometimes together, sometimes separately, painting the sky with shifting light. The seasons would be strange and unpredictable, controlled by the complex rhythm of the star's orbit, and yet these systems exist. We've seen them. The first confirmed circumbinary planet, Kepler 16b, orbits 2 stars roughly 200 light-years away. It's a gas giant, but its presence proved that even binary systems can host planets. Nature doesn't avoid complexity, it embraces it. Some solar systems are made of stars that share planets unequally. In a few, a small companion star passes through the outer regions of a larger star system, disturbing the orbits of planets, scattering comets, or even stealing material to form its own disk. These interactions can destabilize systems, ejecting planets into interstellar space. Others may have stars that pass nearby just once, grazing the outer boundaries of a system and sending objects flying. The galaxy isn't empty, stars move through it, and their gravity sometimes pulls on each other's families of planets. Over billions of years, the architecture of a solar system can change dramatically just from these encounters. The orbits of planets in other systems vary as widely as their distances. Some are tilted, inclined at sharp angles to the plane of their star's rotation. Others are retrograde, orbiting backward relative to their star's spin. This suggests violent pasts, collisions, migrations, gravitational upheavals that have reshaped their paths. Some planets share nearly the same orbit, locked in resonances that keep them from colliding, like synchronized dancers maintaining perfect distance. Others are caught in chains of resonance, where each planet's orbit is tied to the next in mathematical precision. Systems like TRAPPIST-1, for example, show this kind of order. 7 small, rocky planets orbit a dim red dwarf star only 40 light-years away, all packed within a space smaller than Mercury's orbit. Their periods are perfectly interlocked. For every orbit one completes, others complete 2, 3, or more, keeping the whole system stable. It's a miniature clockwork of gravity, fragile but harmonious. There are also systems that seem on the edge of chaos. Planets whose orbits cross or nearly collide. Systems that seem destined for disruption. Some of these may not survive long on cosmic timescales. Gravity can be cruelly precise. A small nudge, a change in resonance, or a close encounter with another star could send a planet tumbling out of its orbit forever. Yet even instability has beauty. It shows that the universe allows experimentation, that solar systems aren't designed for permanence but for variety. The shapes of solar systems are sculpted by time. In their youth, they're messy, filled with dust, debris, and collisions. Planets are still forming, pulling in material, bumping into each other, merging or breaking apart. As they age, they settle, clearing their orbits, finding balance. The final structure, the number of planets, their spacing, their eccentricities, reflects the entire history of that system's formation. Some systems end up orderly, others remain eccentric for billions of years. What we see now across the galaxy is a collection of snapshots, each one frozen at a different stage of its evolution. Some are newborn, still glowing with heat from formation. Others are ancient, their stars dimming, their planets long since locked into quiet stability. There are worlds that orbit so close to their stars that they're tidally locked, showing the same face forever, one side bathed in constant daylight, the other in eternal night. There are planets that orbit so far away that their suns are mere pinpoints of light. In some systems, gas giants dominate, leaving little room for smaller worlds. In others, small rocky planets cluster near the star, while distant belts of ice and dust circle far beyond. Some systems may have multiple belts, asteroid belts, comet reservoirs, rings of debris marking the scars of past collisions. Each pattern tells a story of formation and change. In a few systems, we've even detected exomoons, moons orbiting planets beyond our solar system. They're difficult to find, their signals faint, but their existence adds another layer of complexity. If there are exomoons, there may also be systems with multiple moon-bearing planets, miniature subsystems within systems. The possibilities multiply endlessly. The diversity of shapes we see among solar systems raises a simple question. Why is ours the way it is? Our planets orbit in nearly circular paths, roughly aligned in a single plane. That regularity may be part coincidence, part survival. Systems that remain stable for billions of years are the ones we're most likely to find intact. Perhaps there were once more planets here, ejected or destroyed long ago. Perhaps the order we see now is the result of countless past disruptions that finally settled into balance. When we study other systems, we're also looking backward at our own history, trying to imagine what might have been. Some systems, like HR 8799, have given us glimpses through direct imaging, actual photographs showing planets as small points of light orbiting their star. In those rare images, you can see the faint arcs of their movement over time. It's a reminder that these are real places, not just lines on a chart. Their orbits aren't abstract. They're physical, dynamic, living. The same gravitational rules that keep Earth circling the Sun also keep those distant worlds in motion. The equations are universal, but the outcomes are infinitely varied. Even binary systems, once thought too unstable for planets, have proven capable of hosting them. Some planets orbit both stars, others orbit just one while the second star orbits far away. In a few, the two stars are so close that they act like a single gravitational source, while in others, the companion star moves in wide, slow arcs, tugging gently on the planet's orbits. The result is a dizzying array of configurations, each one stable in its own way, each one a different expression of balance between light and gravity. There are also systems where planets form in places we didn't think possible, around white dwarfs, neutron stars and pulsars. These systems challenge every assumption about how planets form and survive. Some of these worlds may have been captured, others rebuilt from the debris of exploded stars. The fact that they exist at all suggests that planet formation is incredibly resilient. Even in the most extreme environments, the universe finds a way to make worlds. When we think about the shapes of solar systems, we're really thinking about the interplay between chaos and order. Gravity can pull planets into resonance or throw them into exile. Disks can collapse neatly or fragment into clumps. Over time, the systems that survive are those that find equilibrium. But equilibrium doesn't mean uniformity. It can take many forms: a cluster of small planets packed close together, a chain of giants evenly spaced, or a single lonely world orbiting far from everything else. Every arrangement is a possible answer to the same question. How does matter organize itself around light? It's easy to think of our solar system as normal simply because it's familiar, but in the context of the galaxy, it may be the exception. Most of the stars in the Milky Way are smaller and cooler than the Sun. Their planets orbit closer, their years shorter, their systems are more compact, more densely populated. The diversity is so broad that it's hard to define what a typical system even means anymore. The shapes of other systems remind us that normal is a human concept, not a cosmic one. Nature doesn't repeat patterns exactly. It explores every variation. If you could travel between stars, each stop would be a new kind of geometry. Around one star you might find planets locked in tight, synchronized loops, their gravitational tugs keeping them in rhythm. Around another you might find orbits stretched and unstable, worlds sliding through long, lonely arcs. Around yet another you might find chaos, debris, dust, fragments of failed planets colliding endlessly. And still, all of these would be natural, all of them expressions of the same physics. The galaxy is not a machine that produces identical systems. It's a workshop of variation, constantly experimenting, constantly reshaping. As our instruments improve, we'll start to see these shapes more clearly. The James Webb Space Telescope and other future missions are beginning to observe the disks around young stars directly, watching planets carve paths through them as they form. In those disks we can see rings, gaps and spirals, the fingerprints of newborn planets. Some disks have multiple bright bands, suggesting several forming worlds. Others are irregular, distorted, perhaps by the influence of a nearby star or an unseen companion. It's as if we're watching the galaxy sculpt itself in slow motion, each system a work in progress. The shapes of other systems are not just curiosities, they're keys to understanding how planets form, evolve, and survive. By comparing their architectures, we can learn what conditions lead to stability, what lead to chaos, and what might make a system capable of supporting life. A stable orbit, a calm star, a safe distance. These are the ingredients that made Earth possible. Somewhere out there, similar configurations must exist. The galaxy's vast diversity ensures that if it can happen once, it can happen many times. The next time you see an image of the night sky, try to imagine what lies beyond the light. Every star you see could hold a system shaped completely differently from ours. Some might be orderly, others wild. Some might hold dozens of worlds, others just one. The diversity is the beauty. The galaxy isn't filled with repetition, it's filled with imagination expressed through gravity and time. Every solar system is a different melody in the same cosmic symphony. And as you drift further into thought, picture it quietly. Billions of stars, each with its own family of planets, each arranged in its own peculiar way. Some like ours, many not. All turning, all moving, all alive with possibility. The shapes of the other systems are the shapes of the galaxy itself. Varied, unpredictable, endlessly creative. Each one a reflection of the same universe, seen through a different lens of matter and motion. In the quiet language of astronomy, there's a phrase that sounds almost like something from a fairy tale. It's called the Goldilocks zone. The name comes from the old story of the girl who wandered into a house and found 3 bowls of porridge, one too hot, one too cold, and one just right. In science, the metaphor describes a region around a star where the temperature is neither too high nor too low for liquid water to exist on a planet's surface. It's the zone where conditions might be just right for life as we know it. Simple in theory, but the more we've learned about other solar systems, the more complicated that phrase has become. Water, as ordinary as it seems, is the foundation of everything we call life. It dissolves, transports, shapes, and moderates. Without it, the chemistry of life becomes impossible, or at least impossible in any form we recognize. On Earth, every known living thing depends on it. So when astronomers began to search for habitable planets, water became the benchmark. If a planet orbits its star at just the right distance for liquid water to exist, then it might be capable of supporting life. That distance depends on the star's heat. Around a bright, hot star, the habitable zone lies far out. Around a cool, dim star, it hugs close. The balance is delicate. A few percent closer, and the planet might become a furnace. A few percent farther, and it could turn to ice. For a long time, our own solar system was the only example we had. Earth sat neatly in the middle, warm enough to keep its oceans liquid, cool enough to prevent them from boiling away. Venus, closer to the Sun, lost its water long ago. Its thick atmosphere traps heat so efficiently that its surface is hot enough to melt lead. Mars, farther out, is cold and dry, its thin air unable to hold warmth. Between those two extremes lies the narrow strip that made life possible here. The Goldilocks zone was, for a long time, the line between barren and alive. When the first exoplanets were discovered, they didn't seem promising. Most were gas giants orbiting close to their stars, too hot, too large, too hostile for life as we imagine it. But as the list grew, we began to find smaller, rockier worlds. Some of them orbited within their stars' habitable zones. They weren't Earth twins, but they were close enough to make us wonder. The first was Kepler 22b, followed by others, Kepler 62f, Kepler 180f, Kepler 452b. Each one offered a glimpse of a possibility, a place where temperatures might allow oceans to form, where clouds might gather, where rain might fall. Yet the question of habitability is far more complex than a single measurement of distance. A planet's potential for life depends on many things: its atmosphere, its composition, its magnetic field, its rotation, even the behavior of its star. The Goldilocks zone describes only the potential for liquid water, not the certainty of it. A world can be in the perfect orbit and still be lifeless if it lacks the right ingredients. Venus, after all, lies close to the inner edge of our own habitable zone, but its runaway greenhouse effect makes it one of the least hospitable places imaginable. Mars, just beyond the outer edge, once had rivers and lakes, but it lost its atmosphere and froze. Both sit near the right distance, yet neither is habitable today. What the Goldilocks zone really represents is the fragile balance between energy and matter. Every planet receives light and heat from its star, but what it does with that energy depends on its atmosphere and surface. On Earth, our atmosphere acts like a blanket, trapping some of the sun's warmth but letting enough escape to keep temperatures stable. Without it, the planet would freeze. With too much of it, like Venus, the heat becomes unbearable. The chemistry of air, the presence of carbon dioxide, water vapor, and other gases creates a feedback system that can stabilize or destroy a planet's climate. The habitable zone may be a distance, but habitability itself is a process, a long dynamic relationship between a planet and its star. When scientists look at other solar systems, they see stars of every type and size. Small red dwarfs, for instance, are the most common stars in the galaxy. They burn slowly, live for trillions of years, and their habitable zones lie close in, so close that any planet there might be tidally locked, showing the same face to the star forever. One side would be in endless daylight, the other in perpetual night. For a long time, that was thought to make such worlds uninhabitable, but newer models suggest that with a thick enough atmosphere, heat could circulate, softening the extremes. Winds could carry warmth from day to night, creating a band of twilight where temperatures might be stable. In that half-lit zone, life could find a niche. That idea reshaped our expectations. If red dwarfs can host habitable worlds, then the number of potentially life-supporting planets increases enormously. Since most stars in the Milky Way are red dwarfs, that means there could be hundreds of billions of possible Goldilocks planets. But possible is the key word. Red dwarfs are often volatile, especially when young. They emit strong flares and bursts of radiation that can strip away a planet's atmosphere. The same stars that could nurture life could also destroy it. Habitability, it seems, isn't just about distance. It's about endurance. Even around more stable stars, the picture is complicated. A planet's orbit can change over time. Gravitational interactions with other planets can pull it slightly inward or outward, shifting it in and out of the habitable zone. The star itself changes too, growing brighter as it ages. Our own sun has gradually increased its output over billions of years, and it will continue to do so. The habitable zone around it slowly moves outward, meaning that Earth's comfortable position is temporary. In a few 100 million years, the sun's brightness will make our planet warmer, perhaps too warm to sustain oceans. Mars, meanwhile, might thaw enough to become temperate, a brief reversal of roles before the sun grows too hot for either world. The Goldilocks zone isn't fixed. It drifts with time. The atmosphere also determines how far habitability can stretch. A thick atmosphere rich in greenhouse gases can warm a planet farther from its star. A thin atmosphere can make even a well-placed planet freeze. Titan, Saturn's largest moon, lies far beyond the Sun's habitable zone, but it has lakes of liquid methane on its surface because its atmosphere traps enough cold to keep that methane stable. If Titan orbited closer to the Sun, those same lakes would evaporate. The principle is the same: energy balance, chemistry, and stability. When astronomers estimate how many habitable worlds might exist in the galaxy, they start with the number of stars, then the number of planets, and finally the fraction that lie within the Goldilocks zone. The numbers vary depending on the assumptions, but even conservative estimates are enormous. If just 1 in 10 stars has an Earth-sized planet in its habitable zone, that still means tens of billions of potentially habitable worlds in our galaxy alone. And that's just one galaxy among hundreds of billions. The scale is so vast that even if life were incredibly rare, it would still exist somewhere. The challenge is finding those worlds and determining whether they truly are habitable. Light is our only clue. When a planet passes in front of its star, some of the starlight filters through its atmosphere. That light carries fingerprints, the spectral lines of the gases it passed through. By analysing those lines, astronomers can identify whether water vapour, oxygen, methane or carbon dioxide are present. Each molecule tells part of the story. A combination of oxygen and methane, for example, could suggest biological processes, because on Earth, those gases coexist only due to life constantly replenishing them. Detecting such patterns on another world would be one of the most significant discoveries in human history. Yet even then, caution is necessary. Planetary chemistry is complex. Non-biological processes can also produce similar signals. Volcanic activity, ultraviolet radiation, and chemical reactions in the atmosphere can mimic signs of life. The Goldilocks zone might offer the right conditions, but it doesn't guarantee the right outcome. Life, as far as we know, is a rare synthesis of chemistry, stability, and time. The universe provides many laboratories, but we don't yet know how many successful experiments it has run. The more we search, the more we realize that the concept of just right might not be universal. Life elsewhere might not depend on water or carbon or oxygen at all. It might use different chemistries, different solvents, different forms. There could be organisms that thrive in methane lakes, or in the icy crusts of moons, or in the atmospheres of gas giants. The Goldilocks zone, as we define it, might only describe life like ours. The universe might have its own broader definition of habitability. What's just right for us might be irrelevant to something entirely different. Still, the concept serves as a guide. It gives us a place to look, a starting point in a galaxy too large to search blindly. The Goldilocks zone focuses our attention on the places most likely to resemble home. And even if we never find another Earth, the search itself teaches us how special our balance is. It reminds us that the conditions we live under are the result of billions of years of chance, evolution, and stability. A narrow corridor of warmth and light that allowed oceans to form, continents to shift, and life to take hold. Some scientists have begun to expand the idea into the concept of a galactic habitable zone. Just as planets have regions where life can thrive, so might galaxies. In the dense centre of the Milky Way, radiation levels are high, and gravitational interactions between stars are frequent, making it a difficult environment for stable systems. In the outer edges, where there's less heavy material, planets may struggle to form. Between those extremes lies the region where conditions are once again just right. Enough elements to build planets, enough calm for them to survive, enough time for life to develop. The Earth, it seems, lies within this larger Goldilocks zone as well. When you think about it, the question of just right extends beyond physics and chemistry. It's also a reminder of how balance defines everything we experience. The Earth spins fast enough to prevent one side from burning, but slow enough to allow stable days. Its atmosphere is thick enough to hold warmth, but thin enough to let sunlight through. Its tilt creates seasons. Its moon stabilizes that tilt. Its magnetic field shields it from solar winds. Every one of those factors could have been slightly different, and the result would be a different world. Habitability is not a single number. It's a symphony of coincidences held together by gravity and time. The search for Goldilocks worlds is also, in a quiet way, a search for ourselves. Each discovery of a planet in that delicate zone makes the galaxy feel more familiar. It suggests that the conditions that made life possible here might not be unique. Somewhere, perhaps, another world has found its own balance, its own just right. Maybe it has oceans and clouds. Maybe it has creatures adapted to an alien rhythm of light and dark. Or maybe it's silent, its potential unrealized, waiting for time and chemistry to catch up. The beauty of this search lies in its uncertainty. We don't yet know what we'll find. We might discover that life is abundant, scattered across countless worlds. Or we might find that Earth is rare, a singular accident in a galaxy otherwise sterile. Both answers would be profound. To know that we're not alone would change our place in the universe. To know that we are would make our existence even more precious. Either way, the question keeps us looking. Astronomy, at its heart, is the art of noticing patterns in the infinite. The Goldilocks zone is one of those patterns, a gentle reminder that even in a universe ruled by cold physics, there are regions of warmth and balance where life can flourish. We don't yet know how many there are. The numbers may be vast or they may be small. But the act of searching, of trying to find that perfect distance, connects us to the very forces that made us. Every telescope turned toward the stars, every light curve analysed, every faint signal examined. All of it is part of the same quiet human question. How many other places are just right? When you look up at the night sky, the stars seem so far away, but among them there are zones of comfort, regions of balance, invisible lines where warmth and cold meet in harmony. Somewhere in that vastness, there are other worlds turning slowly, their climates held in delicate equilibrium, their oceans, if they exist, reflecting the light of their suns. They don't know we're watching, and we can't yet see them, but they're there, orbiting in their own Goldilocks silence, part of the same galaxy that made us. When you step outside on a clear night and look up, it's easy to forget that you're part of what you're seeing. The stars appear to hang above you like decorations on a ceiling, scattered without order, remote and untouchable. But in reality, you are inside that view, not beneath it, not looking at it from the outside, but woven into it. You're standing on a planet orbiting one of those stars, inside one arm of a vast spiral galaxy called the Milky Way. The lights above you are not just distant fires, they are neighbours. The night sky isn't a view across space so much as a view from within it. We're not spectators in a cosmic crowd, we're part of the crowd itself. Our solar system lives in a quiet region between two spiral arms of the Milky Way, in what's known as the Orion Spur. It's a relatively calm and stable place, not too close to the chaotic centre of the galaxy, and not too far out in the thin, cold edges. That position gives us a kind of cosmic comfort, far enough from danger, close enough to abundance. The stars here are moderately spaced, each separated from its nearest neighbour by several light years. If space were drawn to scale, you could travel for years at the speed of a light before reaching the next star. The distances are enormous, but within those gaps lies the structure of everything we know. The Milky Way itself is a barred spiral, a disk about 100,000 light-years wide and 1,000 light-years thick, with a dense central bulge where stars cluster by the millions. From that bulge, long arms of stars and gas curl outward, like slow-moving rivers of light. Our Sun orbits near the inner edge of one of those arms, taking roughly 230 million years to make a single journey around the galactic centre. In that time, continents drift, species rise and vanish, and civilizations appear and disappear, all while the solar system continues its slow orbit through the galaxy's spiral lanes. If you could look at the Milky Way from far above, you'd see it glowing softly, its spiral arms dotted with bright patches of star formation, regions where clouds of gas collapse to form new suns. In those nurseries, newborn stars light up the surrounding dust, creating vast nebulae that shine in pinks and blues. Some of those stars will burn brightly for only a few million years before exploding as supernovae. Others will smoulder quietly for trillions. Between them float older stars, their light dimmer, their energy nearly spent. The galaxy is an ecosystem of creation and decay, always reshaping itself, always alive. In that context, our Sun is remarkably ordinary. It's a middle-aged star about halfway through its 10 billion-year lifespan. It shines steadily, with the calm yellow glow of a main-sequence star. Around it, 8 planets orbit in quiet harmony, along with countless smaller objects, asteroids, comets, dwarf planets. For us, it's everything. It provides warmth, light, and stability, the foundation of every living thing on Earth. But from a galactic perspective, it's one among hundreds of billions. There's nothing unique about its brightness or its temperature. It's not especially large, nor especially small. It doesn't sit at the centre of anything. It's just one star in a vast stellar population moving along with the rest. That ordinariness, however, is what makes our place so remarkable. It means we're not in a rare or privileged position. The laws that shape our sun shape every other star. The same physics that holds Earth in orbit holds billions of other planets in theirs. We live in a typical solar system, orbiting a typical star in a typical galaxy, and that typicality connects us to everything else. It means that what happens here could happen elsewhere. It means the ingredients for life, for worlds, for stories, are not confined to one place. When you look up, most of the stars you see are part of the same disk we inhabit. The band of light called the Milky Way, stretching across the night sky, is the combined glow of billions of distant suns, blurred together by distance. Through a telescope, that band resolves into countless individual points. Each one is a sun, many with their own planets. It's not an exaggeration to say that the galaxy is filled with solar systems. The space between stars looks empty, but it's full of invisible gravitational relationships. Worlds circling their stars, moons circling those worlds, dust and comets tracing long paths through the dark. The emptiness is an illusion. From our position in the Orion Spur, about 27,000 light-years from the galactic centre, we can't see the Milky Way from the outside, but we can infer its shape from the way stars move. Radio telescopes map the distribution of gas clouds. Infrared observations reveal the structure hidden by dust. The picture that emerges is elegant. A glowing disk, 4 major arms, a central bar, and a halo of dark matter extending far beyond the visible stars. It's in that halo that the galaxy's hidden mass lies, the invisible glue that holds everything together. Though we can't see it, we feel its pull, the quiet background gravity that keeps our sun on its long looping path. The galaxy rotates slowly but inexorably. At the speed of its orbit, the sun travels about 800,000 kilometers per hour, yet from our perspective, everything seems still. The motion is so vast and smooth that we never notice it. We drift with it, like passengers on a ship too large to feel the waves. Around us, other stars move in their own orbits, following curved paths through space. Some move slightly faster, others slower, some rising above the galactic plane, others dipping below. The stars weave past each other over millions of years, their relative positions shifting in a slow cosmic dance. The constellations we recognize, Orion, Cassiopeia, Scorpius, are temporary patterns, their shapes changing imperceptibly with time as the stars move along their individual trajectories. If you could watch the galaxy in time-lapse over hundreds of millions of years, it would look like a living thing. Stars would swirl like luminous particles in a fluid, clustering and dispersing, their orbits overlapping and diverging. The spiral arms would wind and unwind, shifting under the influence of gravity and rotation. New stars would flare into existence as others fade. The Milky Way is not a static structure. It's an ongoing process, a vast, self-sustaining cycle of light. Our neighbourhood within that flow is a peaceful one. The nearest star system, Alpha Centauri, lies just over 4 light-years away, a distance so immense that our fastest spacecraft would take tens of thousands of years to reach it. Yet in galactic terms, that's practically next door. Alpha Centauri is actually a trio of stars, 2 sun-like stars orbiting each other closely, with a small red dwarf companion, Proxima Centauri, circling farther out. Around Proxima, we've detected at least one planet, roughly Earth-sized, orbiting within its habitable zone. It's called Proxima b, and though it's probably tidally locked and exposed to strong stellar flares, it remains one of the most intriguing nearby worlds. That proximity, a potential planet around the nearest star, makes the sky feel less abstract. It's not just theory, it's geography. Beyond our local group of stars, the neighbourhood expands into clusters associations and moving groups, families of stars born together, still drifting through space in loose formation. Many of these clusters are visible from Earth as faint smudges of light. The Pleiades, the Hyades, the Beehive, each contains hundreds of young stars, often still surrounded by the disks of dust that might one day become planets. Over time, these clusters disperse, their members scattering throughout the galaxy. Our Sun likely began its life in such a cluster billions of years ago, surrounded by sibling stars that have since wandered far away. Somewhere in the galaxy, those siblings still exist, indistinguishable now from the rest, their connection to us written only in shared motion and chemistry. When astronomers study the composition of stars, they can sometimes trace those family relationships. Stars born from the same molecular cloud share the same chemical fingerprint, the same proportions of elements forged in earlier generations of stars. By comparing those fingerprints, scientists can identify stellar siblings, even if they're now separated by hundreds of light years. In a sense, we're learning to read the genealogy of the galaxy, to trace the lineage of stars the way we trace family trees. It's another reminder that everything is connected, that our Sun, our planets, and our atoms are part of a continuous story, stretching back to the earliest days of the Milky Way. In the stellar crowd, the variety of stars is immense. Most are red dwarfs, small, cool, and faint, making up about 70% of all stars. A smaller fraction are yellow stars like the Sun. Rarer still are the blue giants, massive and short-lived, blazing fiercely before collapsing in spectacular deaths. There are binary stars, triples, clusters of dozens bound by gravity. There are white dwarfs, the remnants of dead stars, and neutron stars, the collapsed cores of supernovae, and somewhere among them are black holes, invisible yet powerful, bending light itself. The galaxy is not uniform. It's a patchwork of extremes, a mixture of youth and age, brilliance and silence. Our place in that tapestry is modest but significant. The Earth, small as it is, orbits a stable star in a region that has remained calm for billions of years. No nearby supernovae have disrupted our system. No collisions have thrown us off course. That stability has allowed life to evolve and persist. In more volatile regions, near the galactic core or within dense clusters, such stability might be impossible. There, radiation levels are higher, gravitational interactions stronger, and the chances of catastrophic disruption greater. It seems we occupy a sweet spot, not too crowded, not too empty, not too close to danger, not too far from resources. Even on a galactic scale, we live in a Goldilocks zone. The stars that surround us are not evenly distributed. The disk of the Milky Way thickens toward the centre and thins toward the edges. Above and below the disk lies the halo, a sparse region containing older, metal-poor stars and globular clusters. Those clusters, some of the oldest objects in the galaxy, orbit far above the plane, each one a sphere of hundreds of thousands of ancient stars. They are fossils of the galaxy's youth, remnants from the time when it was still forming. Their light reaches us across tens of thousands of light years, carrying the history of the Milky Way's beginnings. The galaxy itself is part of something larger, a collection of galaxies bound together by gravity known as the local group. It includes Andromeda, our nearest large neighbour, as well as the Triangulum galaxy, and dozens of smaller dwarf galaxies. Over billions of years, these galaxies interact, merge, and reshape each other. In about 4 billion years, the Milky Way and Andromeda will collide, their stars passing mostly unharmed, but their structures blending into a single, larger galaxy. From our perspective, the sky will change slowly, subtly at first, then dramatically as Andromeda grows brighter. It's another reminder that even galaxies are not fixed. Everything moves, everything evolves, everything belongs to something larger. When you think about our place in this stellar crowd, it's natural to feel small. But small isn't the same as insignificant. being part of something vast doesn't reduce your importance, it connects you to it. Every atom in your body was forged in ancient stars that lived and died long before the sun existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar furnaces. The light that warms your skin travels from a fusion reaction 93 million miles away, powered by the same physics that governs the most distant stars. The universe doesn't treat us as separate from it. We're made of its substance, animated by its laws. If you could look down on the Milky Way from above, the sun would be invisible to the naked eye. But the fact that we're here means that within one of those faint points of light, consciousness arose, matter becoming aware of itself. That awareness, that ability to look outward and wonder, is also part of the galaxy's story. We are the means by which the Milky Way can see itself. Our place in the stellar crowd is both ordinary and extraordinary. We are not at the centre, but we are part of the pattern. We are made of the same elements that make the stars shine, bound by the same gravity, moving with them through space and time. When you gaze at the night sky, remember that you're not looking at something distant. You're looking from within it. You're in the middle of a spiral of stars surrounded on all sides by light that has travelled for centuries to reach you. The galaxy is not something you visit. It's something you inhabit. Every time you breathe, every time you think, every time you look up, you are participating in its story. The stars above you are not strangers. They are family, ancient, radiant, and infinite in number, sharing the same space, the same galaxy, the same journey through time. If you could step back far enough to see our galaxy as a whole, the Milky Way would stretch before you like a luminous whirlpool of light, its spiral arms sweeping gracefully outward from a bright central core. But we can't stand outside it. We live inside its disk, surrounded by its stars, woven into its structure. From here on Earth, we see only pieces of the whole, the dense band of starlight that crosses the night sky, the faint glow of interstellar clouds, the occasional dim shadow where dust blocks our view. Yet even from this limited vantage point, we can begin to understand what kind of neighbourhood we live in. The Milky Way isn't just a galaxy, it's a city of stars, and like any city, it has its busy districts, its quiet outskirts, its bustling intersections, and its dark, hidden corners. Our sun resides in a relatively calm district, neither too close to the crowded galactic centre, nor too far out in the thin, sparsely populated edge. This region, known as the Orion Spur, lies between two of the Milky Way's major spiral arms, the Sagittarius arm and the Perseus arm. It's a minor structure, a kind of side street branching off the main spiral avenues, yet it's home to thousands of stars, clusters and nebulae. It's where our solar system orbits, taking roughly 230 million years to complete one lap around the galactic centre. During that journey, we pass through regions of varying density and activity, clouds of gas, open clusters, voids, and streams of dust, all moving and shifting together in an immense, slow-motion ballet. The Milky Way structure is shaped by gravity and time. Its spiral arms aren't solid objects but patterns, waves of density that move through the disk, compressing gas and triggering star formation as they go. The arms appear bright because that's where new stars are born, their light illuminating the surrounding clouds. Between the arms, the galaxy is quieter, filled with older stars and thinner gas. Our Sun, being about 4.6 billion years old, likely formed in one of those brighter regions long ago and has since drifted into calmer territory. That motion continues even now, carrying us slowly through the galactic plane. If you could look out from our position toward the galactic centre, you'd see a dense cluster of stars packed tightly together. There in the heart of the Milky Way lies a supermassive black hole called Sagittarius A, containing the mass of 4 million suns. Around it, stars orbit at incredible speeds, some moving so fast that their paths have been measured to trace the black hole's influence directly. The central bulge glows, with the combined light of billions of ancient stars, many older and redder than our Sun. It's a crowded, turbulent place where gravity reigns and radiation is strong. Life as we know it would struggle there. But it's also where the history of the galaxy is written, a record of star formation stretching back to its earliest days. Moving outward from the centre, the density of stars decreases. The spiral arms wind around like long glowing rivers, filled with hot blue short-lived stars and the nebulae that gave birth to them. These regions are the nurseries of the galaxy. Within them, vast clouds of molecular hydrogen collapse under their own weight, forming clusters of new stars. The most massive stars live fast and die young, exploding as supernovae and enriching the surrounding space with heavier elements, the building blocks of planets, moons, and life. The cycle continues endlessly. Gas becomes stars, stars create elements, and those elements form new systems. The Milky Way is not static. It's a living structure, always recycling its material, always creating new worlds from the remnants of old ones. Our part of the galaxy is comparatively peaceful. The Orion Spur contains several familiar features of the night sky. The Orion Nebula, visible as a faint patch of light in the sword of Orion's constellation, is a stellar nursery, a region where new stars and planetary systems are forming right now. The Pleiades, or Seven Sisters, are a cluster of young stars still surrounded by traces of the dust from which they were born. The Horsehead Nebula, the Rosette Nebula, the Lagoon Nebula. All of these are nearby landmarks within our galactic neighbourhood, each one a signpost of creation. When we look at them, we're seeing the process that formed our own Sun billions of years ago, continuing elsewhere in the same galaxy. The stars nearest to us form what astronomers call the local bubble, a region of relatively low-density gas about 1,000 light-years across. It's like a hollow carved out of the galactic disk, likely formed by ancient supernovae whose shockwaves cleared away the surrounding material. Our Sun happens to be travelling through this bubble, and that's one reason our sky is so transparent. In other regions, thicker clouds of dust would obscure much of the starlight, but here the view is clear. The edges of the local bubble are dense and bright in ultraviolet light, where gas from old supernova remnants continues to glow faintly. We are, in a sense, moving through a region shaped by the death of stars long before ours was born. Beyond our immediate surroundings lies the broader galactic neighbourhood, a region encompassing tens of thousands of light-years and millions of stars. It's organised, though not rigidly. The galaxy's rotation keeps everything in motion, but gravitational interactions constantly reshape it. Stars drift, clusters dissolve, spiral arms shift. Over time, even the Sun's orbit changes slightly, rising and falling through this galactic plane like a slow wave. These oscillations take tens of millions of years and may influence events on Earth in subtle ways. Some researchers have speculated that as we pass through denser regions of the disk, the increased cosmic radiation or gravitational disturbances could affect comet activity, or even climate, though such effects remain uncertain. What's certain is that our solar system doesn't move through empty space. It moves through a dynamic, ever-changing environment. The Milky Way's disk isn't uniform in thickness. In some regions it's denser and brighter, in others thinner and quieter. Surrounding the disk is a halo of old stars and globular clusters, ancient spherical gatherings of hundreds of thousands of suns. These clusters orbit the galaxy like satellites, relics from its earliest days. They are fossils of formation, holding clues to how the Milky Way grew from smaller galaxies billions of years ago. Some of those smaller galaxies were absorbed entirely, their stars now part of our own halo. In fact, the Milky Way continues to consume small galaxies even now. Several dwarf galaxies orbit us, their stars being gradually stripped away by our gravity, their material merging into our disk. The Sagittarius dwarf galaxy, for example, is in the process of being torn apart, its remains stretched into long tidal streams that wrap around the Milky Way like ribbons of faint light. The halo also contains something we can't see directly, as dark matter. Though invisible, it makes up most of the galaxy's mass, extending far beyond the luminous disk. Without it, the stars in the outer regions would drift away. The dark matter's gravity holds everything together, shaping the motion of stars and the curvature of the galaxy itself. We don't yet know what dark matter is, but we know it's there, like an unseen foundation beneath the city of stars. Its presence defines the boundaries of our galactic neighbourhood more than anything we can see. Every neighbourhood has its communities, and ours is no different. The Milky Way is part of a small collection of galaxies known as the Local Group, about 50 or so galaxies bound together by gravity. The two largest are the Milky Way and the Andromeda Galaxy, followed by the smaller Triangulum Galaxy and numerous dwarf companions. These galaxies orbit one another in slow, complex paths, interacting through their mutual gravitational pull. In about 4 billion years, the Milky Way and Andromeda will collide and merge, forming a new, larger galaxy. From Earth, the event will unfold over millions of years. To future observers, the night sky will fill with the growing disk of Andromeda, until the two galaxies blend into a single luminous structure. Stars will rarely collide directly, but their orbits will change, creating new patterns and triggering bursts of star formation. Even after that, the new galaxy will continue to evolve, shaped by time and gravity into something different, something new. Closer to home, our galaxy's nearest neighbours include several dwarf galaxies, the large and small Magellanic Clouds, visible from the southern hemisphere as faint cloud-like patches of light. They orbit the Milky Way at distances of about 160,000 and 200,000 light-years, respectively, and are themselves filled with young stars and active star-forming regions. They are reminders that galaxies, like stars, rarely exist alone. Gravity binds them into families, into groups and clusters, each influencing the others. Our galactic neighbourhood is part of a hierarchy, small systems orbiting larger ones, which in turn belong to even larger structures. The Local Group itself sits on the edge of the Virgo supercluster, a sprawling network of thousands of galaxies connected by filaments of dark matter and gas. And beyond that, there are superclusters, walls, and voids stretching across the observable universe. Our galaxy is just one light in a web of billions. Despite the immensity of that structure, our local region is relatively tranquil. The Milky Way isn't in a particularly dense cluster. It drifts in a quiet corner of space, far from the violent collisions that happen in crowded galactic clusters where galaxies tear each other apart. That serenity may have helped make our existence possible. In calmer regions, stars can live long, stable lives. Planetary systems can form and persist without constant disruption. Somewhere amid that calm, one star gave rise to a world where matter learned to think, to wonder, to ask where it came from. The galactic neighbourhood is not static. It's a landscape of motion. Every star, every cluster, every cloud of gas moves along its own trajectory. Over time, those paths create patterns, streams, filaments, and bridges connecting one part of the galaxy to another. The Sun follows its orbit in the disk, accompanied by other stars moving in roughly the same direction. If you could watch them all at once, they'd look like birds in slow flight, gliding together through the dark. Occasionally, two pass close enough to influence each other's paths, their gravity creating ripples that spread through the surrounding space. Over billions of years, these interactions shape the galactic disk, thickening it, stirring it, and ensuring that no star remains truly isolated forever. The neighbourhood around our Sun extends much farther than we can yet explore. The Oort cloud, a vast spherical shell of icy bodies, marks the outermost edge of the Sun's gravitational influence. Beyond it lies interstellar space, where the solar wind meets the thin gas that fills the galaxy. Our spacecraft, Voyager 1 and Voyager 2, have crossed that boundary, becoming our first emissaries to the interstellar medium. They are now part of the Milky Way itself, drifting among the stars, carrying messages from one small planet to the rest of the galaxy. Their journey reminds us that we're connected to this neighbourhood not just by gravity, but by curiosity, by the urge to reach outward, to see what lies beyond the next light. When we imagine our galactic neighbourhood, it's tempting to think of it as a map, a set of positions and distances. But it's more accurate to think of it as a dynamic web of relationships. Stars form together, drift apart, influence each other, merge and evolve. The Milky Way's shape is the sum of all those relationships. Our sun's orbit crosses paths with countless others, and though we never feel it, those encounters shape our motion. We're part of a continuous conversation of gravity that's been going on for billions of years. To understand our place in the galactic neighbourhood is to understand that we're both tiny and central, not in position, but in participation. Every planet, every star, every particle of dust contributes to the galaxy's shape. The light that leaves our sun travels outward, becoming part of the Milky Way's collective glow. The atoms that once formed other stars now form us, and someday, long after the sun fades, they'll return to space and become part of something new. The neighbourhood isn't just where we live, it's what we are. When you look at the Milky Way stretching across the sky, you're seeing the inside of your own galaxy, the lights of distant neighbours, the scattered glow of your own cosmic city. Each of those stars, even the faintest, has its own orbit, its own story, its own system of planets. Together, they make up the fabric of our galactic neighbourhood, a vast connected community of light and motion. And we, circling one ordinary star on one small planet, are part of that community, travelling with it through space, contributing our small flicker of awareness to its endless, luminous journey. Every star you see in the night sky was born out of dust. That simple fact hides one of the most intricate processes in the universe, the making of planets. They do not appear fully formed, shining and spinning in perfect orbits. They are built slowly from the leftover materials of star formation, from clouds of gas and grains of rock that take millions of years to organize themselves into worlds. Every solar system begins as a kind of cosmic workshop, a factory where gravity and motion turn chaos into order, where light creates the conditions for matter to coalesce, and where something as solid as a planet emerges from something as diffuse as starlit dust. It begins in the dark. Deep inside giant molecular clouds, vast regions of cold hydrogen and dust stretching for dozens of light years, small pockets begin to collapse under their own gravity. These clouds are scattered across the spiral arms of galaxies, especially where density waves compress gas and trigger new generations of stars. From the outside, they appear as dark shapes silhouetted against the brighter background of the Milky Way. Within them, the temperature can be only a few degrees above absolute zero. In those conditions, dust grains clump together, forming denser knots, and eventually gravity takes over completely. The knots collapse, spinning as they fall inward, flattening into disks. At the centre of each disk, the pressure builds until hydrogen atoms begin to fuse and a new star is born. But the star is not the end of the story, it's the beginning. The disk that surrounds it, the protoplanetary disk, is where planets are made. It's made of the material that didn't fall into the star, tiny silicate particles, ice, carbon compounds, metals, and gases like hydrogen and helium. The disk is enormous, stretching across billions of kilometres, and though it looks smooth from afar, up close it's turbulent and alive with motion. Dust collides and sticks, forming clumps. Those clumps grow into pebbles, then rocks, then larger bodies called planetesimals. Each step is precarious. Collisions can build or destroy depending on their speed. Too fast and the impact shatters the objects. Too slow and they simply bounce apart. Only within a narrow range of velocities can they merge. Over time, a few grow large enough for their gravity to dominate, pulling in more material and sweeping their orbits clean. These are the seeds of planets. In the early stages, the disk is thick with dust and gas, and radiation from the newborn star begins to sculpt it. The inner regions, close to the heat, become dry and rocky. The outer regions, colder and more distant, allow ices to survive. This difference defines the architecture of a solar system. Inside what astronomers call the frost line, materials like water, methane, and ammonia can't remain solid. They evaporate into gas. Beyond that line, those same substances freeze and accumulate. The result is a natural divide, smaller rocky planets near the star and larger icy or gaseous ones farther out. Our own solar system follows this pattern. Mercury, Venus, Earth, and Mars close in. Jupiter, Saturn, Uranus, and Neptune farther away. But the process is far from orderly. The young star often releases bursts of energy, called T-Tauri winds, that blow through the disk, stirring it and pushing lighter material outward. Magnetic fields twist and shift, creating eddies and shocks. The disk itself is constantly evolving. Gas flows inward and outward. Dust grains drift and settle toward the mid-plane, forming a thin, dense layer where planet formation accelerates. In that layer, gravity begins to dominate over turbulence. The larger clumps attract smaller ones, and soon the disk contains hundreds of growing bodies, all orbiting and interacting, colliding and merging in slow, silent violence. In the first few million years, these planetesimals become protoplanets, ranging from tens to hundreds of kilometers across. Their collisions release enormous amounts of energy, heating their interiors and differentiating their structures. Heavy elements sink toward their centers, forming cores, while lighter materials rise to the surface. Some of these protoplanets grow fast enough to capture gas from the surrounding disk, becoming giants. Others remain small and solid. The balance depends on timing. If a protoplanet forms early, while the disk still contains plenty of gas, it can grow into a massive gas giant. If it forms late, after the gas has dissipated, it remains a rocky or icy world. The clock of planet formation runs on millions of years, but the outcome depends on the order of events within that brief window. In the outer regions of the disk, where ices are plentiful, growth is faster. Frozen water and methane stick easily, and the cold environment allows more material to accumulate. That's why gas giants form farther from their stars. Their cores reach a critical mass, usually about 10 times the size of Earth, and their gravity begins to pull in vast envelopes of hydrogen and helium. In just a few 100,000 years, they balloon into giants. Jupiter and Saturn likely formed this way, growing quickly enough to capture most of the gas in their part of the disk before it was blown away. Closer in, where ices are rare and temperatures are high, planets grow more slowly and remain smaller. As the planets form, they sculpt the disk. Their gravity clears gaps along their orbits, creating the rings and lanes that telescopes like ALMA, the Atacama Large Millimeter Array, can now see in astonishing detail around young stars. These images show disks with bright and dark bands, each one marking the influence of a forming planet. It's a process both violent and delicate. Collisions on one scale, balance on another. The forming planets interact gravitationally, sometimes pushing each other into new orbits, sometimes merging, sometimes flinging one another out into interstellar space. Many of the free-floating, rogue planets drifting between stars may have begun in systems that couldn't contain them. Eventually the disk begins to thin. The young star's radiation pushes away the remaining gas, and the collisions slow. What remains is a newly formed solar system, planets, moons, asteroids, and comets, all following paths defined by the chaotic history of their creation. The shapes and spacing of their orbits carry the memory of their formation. Gaps in asteroid belts, tilted orbits, and the presence of moons all record the gravitational jostling that occurred during those early years. In a sense, every solar system is a fossil, preserving the outcome of a process that began in darkness and ended in light. When we look at protoplanetary disks around other stars, we're seeing versions of that process still unfolding. The star Tauri, for instance, about 450 light-years away, shows a young disk with clear rings and gaps, evidence of planets forming even now. The entire system is less than 1 million years old, yet already its architecture is visible. Other disks, like those around TW Hydrae and Beta Pictoris, show similar patterns: spirals, cavities, asymmetries, all signs of gravity sculpting matter into worlds. Observing them is like looking backward in time, catching the Milky Way in the act of making planets. What's extraordinary is how common this process is. Wherever we look, we find disks around young stars. It seems that planet formation is not rare or exceptional, but a natural outcome of star birth. Every generation of stars produces a new generation of worlds. The materials used are recycled from earlier generations, atoms forged in ancient stars, scattered by supernovae, mixed into new clouds, and shaped again by gravity. The calcium in your bones, the carbon in your cells, the oxygen you breathe, all of it was once part of that process. The galaxy is, quite literally, a planet factory. It makes worlds the way trees make leaves, continuously, effortlessly, as part of its nature. But even factories have accidents. Not every forming planet survives. Some fall into their stars, consumed before they can stabilize. Others collide and shatter, sending debris into orbit that may later form moons or rings. In some systems, large planets migrate inward, destabilizing smaller ones. The hot Jupiters discovered around other stars are likely the result of such migrations. Giants that formed far out and then spiraled inward, sweeping away other worlds in their path. These movements leave lasting scars on their systems, altering orbits, changing climates, even deciding which planets remain habitable. Planet formation is creative, but it's also destructive. The beauty we see in finished systems hides a history of upheaval. Over time, the young planets cool, their crusts solidify, atmospheres stabilize, oceans, if they exist, condense or evaporate. Moons form from leftover debris or from captured bodies. Comets and asteroids remain as relics, frozen time capsules containing material from the early disk. In our own system, those remnants still carry the chemical fingerprints of the solar nebula that gave birth to the Sun and planets 4.6 billion years ago. Meteorites that fall to Earth contain grains older than the solar system itself, fragments of ancient stars that were part of the raw material from which everything here was made. Holding one is like touching the history of the galaxy in physical form. The timescales involved in these processes stretch far beyond human imagination. The initial collapse of a gas cloud might take 1 million years. The formation of planetesimals could take another 1 million. The full assembly of a stable planetary system might take tens of millions more. And even after that, evolution continues. Planets migrate, atmospheres change, impacts reshape surfaces, and orbits shift. Our own solar system, though ancient, is still evolving. Asteroids collide, comets enter from the Oort cloud, and the planets slowly alter each other's orbits through gravitational nudges. Stability in cosmic terms doesn't mean stillness, it means rhythm, motion sustained over time. Modern astronomy is beginning to study these processes in detail, not just by observing distant disks, but by analysing the chemistry of the materials involved. Telescopes like ALMA and the James Webb Space Telescope can detect molecules in these forming regions: water vapour, carbon monoxide, methanol, even complex organic compounds. These molecules are the seeds of life, forming before planets are even complete. That means the ingredients for biology may be common in the galaxy, built into the process of planet formation itself. Life may not need a special set of conditions, it may be a natural byproduct of chemistry wherever planets form. What's most striking is how similar these processes are everywhere we look. The physics doesn't change, the details differ, the mass of the star, the composition of the disk, the timing of the collapse, but the underlying mechanism is universal. From one edge of the galaxy to the other, the same pattern repeats. Clouds collapse, disks form, dust turns to rock, and rock turns to worlds. The variety we see in planetary systems, their different shapes, sizes and architectures, all arise from the same simple ingredients and rules. The diversity is immense, but the origin is shared. If you could watch a planet being born, it wouldn't look like creation as we imagine it. It would look like dust and gas swirling in slow motion, light scattering through a cloud, particles colliding silently. Over time, the faint glow would sharpen as the star ignites, casting light on its forming worlds. You'd see bright arcs where new planets clear paths through the disk, their orbits shimmering with reflected light. Eventually the disk would fade, leaving behind a system of planets circling a newborn sun, another addition to the galaxy's endless collection. Somewhere in our galaxy, that process is happening right now, countless times over. In the dark clouds of Orion, in the spiral arms of Cygnus, in the quiet reaches of Taurus, new stars are forming, and around them, disks of dust are beginning to spin. Each disk holds the potential for dozens of worlds, for moons, for rings, for everything that might follow. Most will never be seen by human eyes. They'll orbit their stars for billions of years, unseen, unknown, but real. The galaxy keeps making them, patiently, silently, filling itself with worlds. The next time you look up and see the Milky Way stretching across the sky, imagine what's hidden within that band of light. Behind every visible star there are planets forming, planets cooling, planets aging. The stars are the forges, and their disks are the assembly lines. The materials are simple: hydrogen, helium, carbon, oxygen, silicon, iron. But the result is complexity beyond measure. Every world, every rock, every grain of sand on every planet began as dust in a disk. The galaxy is not just a collection of stars, it's a network of ongoing creation. It builds, recycles, and builds again. And here we are, standing on one of its finished products, a planet that began as dust around a young star billions of years ago, a planet that cooled, stabilized, and eventually became capable of supporting thought. To understand planet formation is to understand where we came from. The same forces that shape the Earth are shaping worlds right now, all across the galaxy. Every night the light from those forming systems travels through space, carrying the story of creation in the faintest wavelengths. The universe doesn't hide its process, it just unfolds too slowly for us to see it. But the evidence is everywhere, in every world that spins beneath its star, in every moon that reflects its light, in every fragment of dust still drifting between them. The galaxy is a factory, and its product is possibility. Some planets have no sun. They drift alone through the galaxy, cold and silent, moving through the dark with no orbit, no sunrise, no horizon. Astronomers call them rogue planets, or free-floating planets, but there's something poetic about thinking of them as wanderers, orphans of the cosmic process that creates and destroys worlds. They're as real as any planet with a star, as massive, as physical, as gravitationally bound to themselves, but they travel without the warmth of a parent star to hold them. The galaxy, for all its billions of shining suns, also contains these dark travellers, planets lost between the lights, invisible except when they briefly betray their presence by bending or blocking the light of a distant star. For most of history, the idea of such planets seemed unlikely. How could a planet exist without a sun? A planet, by definition, was something that orbited a star. It seemed impossible that a world could simply float through space unattached. But as our understanding of planetary formation deepened, the idea became not only possible, but inevitable. Solar systems form through turbulence and violence. Planets collide, migrate, and scatter. gravity reshuffles orbits constantly in the early stages. In those interactions, it's easy for a smaller body to be flung away, ejected from the system entirely. Once it's gone, there's nothing to slow it down. It drifts into interstellar space, carrying with it whatever atmosphere, moons, or rings it might have once had. The Milky Way, it turns out, could be filled with billions of such orphans. The first hints of rogue planets came not from direct observation, but from the mathematics of planetary dynamics. When computer models simulated the early evolution of solar systems, ejections happened frequently. Even in stable systems like ours, gravitational interactions among massive planets could, in certain circumstances, send smaller ones flying out. Jupiter, with its immense gravity, acts as a cosmic gatekeeper in our own solar system. It protects Earth from many incoming comets, but in the distant past, it may also have been responsible for ejecting other bodies. The model suggested that for every stable planet that remains bound to its star, several might be thrown away. If that ratio holds across the galaxy, then there could be more free-floating planets than stars, a hidden population of worlds wandering in the dark. Evidence began to appear in the data. In 2011, astronomers using a technique called gravitational microlensing detected signals that suggested the presence of Jupiter-sized objects not bound to any star. Microlensing occurs when a massive object passes in front of a background star, bending and magnifying its light through gravity. The duration and shape of the light curve reveal the mass and nature of the lensing object. In these cases, the signals matched planets. Not stars, not brown dwarfs, but planetary masses drifting through space. Subsequent studies confirmed the finding. The galaxy contains many such wanderers. Later observations extended the range to smaller, Earth-sized, or even Mars-sized bodies. These planets, though unilluminated, leave fingerprints in the way they bend starlight. What these worlds are like is a question both scientific and imaginative. Without a star to warm them, their surfaces would be cold beyond comprehension, frozen to temperatures only a few degrees above absolute zero. Yet some might not be entirely dead. If they are large enough, internal heat from radioactive decay or residual formation energy could keep their interiors warm. If they have thick atmospheres of hydrogen or methane, that heat could be trapped, maintaining pockets of warmth. A planet with subsurface oceans, insulated beneath layers of ice, could in theory remain liquid even in interstellar space. There's speculation that some of these rogue planets might harbour internal oceans, like those on Europa or Enceladus, warmed by their own cores. If so, life, microbial, slow, adapted to darkness, might not need starlight at all. It's a strange thought, that life could drift between stars, surviving on worlds that never see dawn. Yet when we look at our own solar system, we see hints that it might not be impossible. The icy moons of Jupiter and Saturn are far from the Sun, yet beneath their frozen crusts they hold vast oceans of liquid water. Tidal forces from their parent planets keep those oceans from freezing solid, generating heat through friction. A rogue planet wouldn't have tides from a nearby giant, but it could have its own radioactive warmth, or heat left from its violent birth. It's not the kind of life we imagine under sunlight, but perhaps something could persist. Slow, ancient, unaware of the stars above it. The existence of rogue planets challenges the way we think about what a planet is. For centuries, we defined them by their relationship to stars. But perhaps that relationship is only temporary. If a planet can survive the loss of its parent, if it can drift for billions of years without disintegrating, then it's not dependent on that light. It's independent, self-contained, a world in its own right. The galaxy, then, isn't just a collection of solar systems. It's also a vast sea of solitary planets, moving through the dark between the stars. Some of these orphans may have had violent pasts. They might have been formed in multiple star systems, where complex gravitational interactions make stable orbits rare. In such systems, one star passing too close could easily tear a planet away. Others might have been caught in near collisions between systems, flung into interstellar space during close encounters. Some may even have formed in isolation, directly from collapsing clumps of gas too small to ignite as stars. In that case, they would be planetary by mass but stellar in origin, failed stars rather than lost planets. Nature doesn't draw sharp lines between categories, it creates continuums. The boundary between small star, brown dwarf, and large planet is blurred, and in that blur lie countless variations. It's difficult to detect these objects directly, because they emit almost no light. The coldest among them shine faintly in infrared, their heat left over from formation. Telescopes like the James Webb Space Telescope are beginning to detect a few of these faint sources. Lonely, Jupiter-sized objects glowing softly in the infrared spectrum, drifting through nearby regions of the galaxy. Each detection adds to the growing understanding that solitude is not rare in the cosmos. For every planetary system that survives intact, many more dissolve into the galactic background, their fragments joining the population of wanderers. There's a haunting beauty in imagining these worlds. A planet without a sky, without sunrise, without seasons. Its surface shrouded in perpetual night, illuminated only by the faint glow of its own internal warmth. Perhaps dimly lit by starlight so distant it would appear as a single point. Winds might still blow there, driven by temperature gradients in the thin atmosphere. Mountains could rise and erode, glaciers could crawl across plains of ice. Meteor impacts could scar the surface. Even without sunlight, time would still move, physics would still apply. The silence would be complete, but not lifeless, just slow, vast, and unending. In a way, rogue planets are reminders of the universe's balance between creation and loss. Every solar system begins with more material than it can hold. Gravity pulls inward, but momentum and chance scatter things outward. Some objects find stable orbits, others are thrown away. The galaxy doesn't waste them, it simply redistributes them. These orphans become part of the galactic medium, travelling through its dark corridors, perhaps occasionally passing close enough to a star to be captured again. It's possible that some planetary systems have adopted such wanderers, pulling them into new orbits. If that happens, a planet might experience a second birth, a world that once drifted through the dark finding a new sun. Such captures would be rare, but not impossible. The galaxy is full of motion, and over billions of years paths intersect. A rogue planet passing close to a young star system could slow down enough to be caught, joining a new family. Its surface, long frozen, might thaw under new sunlight, revealing landscapes untouched for eons. It's an idea that stretches imagination, but the physics allows it. Gravity doesn't forget, and time gives it endless opportunities. The number of these orphan planets is still uncertain, but estimates suggest there could be as many as 1 trillion in our galaxy alone. That's 1 trillion worlds without stars drifting in silence. Most will remain invisible forever, but statistically some must pass relatively close to us, within a few light years, even within our neighbourhood. Occasionally, one might even pass through the outer regions of our solar system, slipping through the distant Oort cloud before continuing on its way. The odds of such an event are small, but over billions of years, not zero. The galaxy's vastness makes encounters rare, but its timescale makes them inevitable. When we speak of rogue planets, we often imagine them as exiles, as worlds that have lost something. But another way to see them is as free agents, unbound, self-sufficient, moving through the galaxy's gravitational fabric with independence. They carry with them the same elements that make up stars and living things, the same materials that built Earth. In their isolation, they are part of the same system that connects everything else. The Milky Way is not a collection of separate systems, but a network of matter in motion, and these wanderers are its quietest participants. Studying them is difficult, but even indirect knowledge changes how we understand the galaxy. It reminds us that not everything that exists must shine. Most of the universe's matter is dark, unseen, unfelt, known only through its influence. Rogue planets fit into that pattern. They are the hidden mass of the galaxy's visible side, contributing to its gravity, shaping its structure, travelling endlessly without revealing themselves. They are as numerous as stars, but mostly invisible, adding a layer of mystery to the fabric of space. In recent years, scientists have even speculated that some rogue planets might host their own moons, captured during ejection or formed before it. A planet and moon drifting together through interstellar space. A double world, orbiting nothing but each other. The tidal forces between them could generate heat, keeping their interiors active. Such systems could remain geologically alive long after leaving their stars. If that's true, then the universe might hold pairs of wandering worlds, bound together in the dark, their mutual gravity providing the only connection they have left. The existence of orphans and wanderers also reframes how we think about planetary survival. When stars die, their planets face uncertain fates. As a star expands into a red giant, it can engulf its inner worlds, while outer ones drift outward. When the star sheds its outer layers and becomes a white dwarf, some planets remain, circling the faint remnant, but others escape entirely. The galaxy's population of rogue planets likely includes many such relics, survivors of stellar death. They are reminders that even after stars fade, their worlds endure. Light may end, but matter continues. When we think about the Milky Way as a community of stars and systems, it's easy to imagine that everything revolves around light. But half of its story happens in darkness. Between the shining systems lies an invisible population, billions of worlds moving silently through the interstellar medium. They don't orbit or radiate, but they're part of the same galactic story. They drift through the magnetic fields, through the diffuse gas, through the gravitational wells of spiral arms, contributing to the galaxy's structure in ways we can't yet measure directly. The Milky Way's beauty lies not just in its lights, but in what those lights conceal. If you could float in the space between the stars, far from any sun, the darkness would be total, but it wouldn't be empty. Around you, invisible, would be these orphan worlds, each following its own path, some no larger than Earth, some as massive as Jupiter, some frozen solid, others still glowing faintly from internal heat. They would pass in silence, separated by light years, unseen but real. You might never notice one unless it blocked a distant star, but they'd be there, the unlit population of the galaxy, the forgotten products of its restless creativity. When astronomers speak of the galaxy's hidden structure, they include these worlds in their models. They affect the way mass is distributed, the way light bends, the way stars move through the disk. They're part of the texture of the Milky Way just as much as the bright stars we see. Every one of them was once part of something larger, a disk, a cluster, a forming system, and every one of them carries that history with it. Even in isolation, they remain connected by origin. It's a quiet comfort to think that the galaxy holds not just brilliance, but silence. That for every star shining in the night sky, there may be a dozen worlds travelling unseen. They are not lost. They are part of the same ongoing motion, the same cosmic flow that includes us. Somewhere, even now, a rogue planet might be passing through a region of space we'll cross millions of years from now. The galaxy's paths are long, but they intersect endlessly. The orphans and wanderers remind us that not all light needs to be visible to exist. Not all worlds need a sun to belong, and not all stories need to be illuminated to matter. They drift between stars, quiet witnesses to the history of creation, carrying the same dust that made us, continuing the same journey through the galactic night. When astronomers talk about life elsewhere in the universe, they often begin with caution. No one has found it, no one has proven it, and yet the more we learn about the galaxy, the harder it becomes to believe that life is confined to one small planet, orbiting one ordinary star. The Milky Way is a vast collection of billions of suns, each with planets of its own, each offering unique conditions, histories and possibilities. The elements that make life possible on Earth, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are not rare. They are among the most common in the universe. They form molecules easily, bind together into structures, and react in patterns that repeat across light years. What is rare, perhaps, is the sequence of circumstances that turn those molecules into something that breathes, grows, and thinks. But given enough worlds and enough time, even rare things become inevitable. To look for life among the stars, we first need to define what we mean by it. On Earth, life is chemistry guided by energy. It takes in matter, transforms it, and uses it to maintain order against the chaos of entropy. It adapts, reproduces, and evolves. All of it depends on a balance between stability and change. Enough energy to drive reactions, but not so much that molecules are destroyed. That balance comes naturally here, under the warmth of the sun and within the shelter of our atmosphere. But there are many ways to achieve the same principle. Life might not always need sunlight. It might use chemical gradients, geothermal heat, or even radiation as its power source. If so, it could exist in environments we once thought impossible. The search for life beyond Earth began close to home. Mars was the first candidate. For centuries it captured human imagination. Telescopes revealed surface features that some mistook for canals, straight lines that hinted at civilization. Those lines turned out to be illusions, but the fascination remained. When robotic explorers arrived, they found a world both familiar and alien. Dry deserts, thin air, freezing temperatures, but also evidence of rivers and lakes long vanished. The rocks carried traces of ancient water, and some minerals could only have formed in its presence. Mars might once have been habitable, and perhaps deep underground parts of it still are. The Viking landers in the 1970s performed experiments to detect life directly, but the results were ambiguous. Decades later, rovers like Curiosity and Perseverance discovered organic molecules in Martian soil, not proof of life, but proof that the building blocks are there. Beyond Mars, attention turned to the outer solar system, where icy moons conceal oceans beneath their crusts. Europa, orbiting Jupiter, has a surface of cracked ice and a global ocean beneath it, warmed by tidal forces. Geysers of water vapour erupt from its surface, hinting at liquid reservoirs below. Enceladus, a smaller moon around Saturn, shows similar plumes rich in organic compounds. Titan, another of Saturn's moons, has rivers and lakes of methane with a thick atmosphere and complex chemistry. None of these worlds receive much sunlight, yet each has the essential ingredients for life: liquid, chemistry, and energy. If microbial ecosystems exist in their hidden oceans, then life may not be confined to the narrow region of a star's warmth. It might thrive anywhere matter and energy can interact in stable ways. Once we realized that the galaxy is filled with planets, the question of life expanded beyond our solar system. The discovery of exoplanets transformed speculation into calculation. With billions of planets orbiting billions of stars, even a tiny fraction capable of supporting life would mean an immense number of living worlds. The challenge is not believing they exist, but finding evidence. Light becomes our only messenger. When a planet passes in front of its star, a small portion of starlight filters through its atmosphere. Embedded in that light are spectral signatures, lines corresponding to specific gases. On Earth, the combination of oxygen, methane, and water vapour in our atmosphere is sustained by life. Detecting a similar combination elsewhere would be a powerful hint. Astronomers call such markers biosignatures, and they are the fingerprints we search for across the stars. The James Webb Space Telescope has begun to examine exoplanet atmospheres with unprecedented sensitivity. It has already detected carbon dioxide, methane, and water vapor on several worlds. Some are giant planets, unlikely to host life as we know it, but others are smaller and closer to Earth in size. Future instruments will refine those measurements, targeting planets in the habitable zones of nearby stars. The hope is not to see life directly, but to recognize its chemical traces, patterns that cannot be explained by geology or physics alone. The discovery of even one planet with a clear biosignature would be a turning point, proving that Earth is not unique. But even if such signals never appear, the possibility remains immense. The Milky Way contains hundreds of billions of stars, and each star is surrounded by space dense with chemistry. Interstellar clouds contain amino acids, alcohols, and sugars, organic molecules formed naturally in the cold between stars. These molecules rain down on forming planets, becoming part of their soils and oceans. Life on Earth may have begun this way, seeded by interstellar chemistry. If that's true, then every planet with similar conditions begins its story already halfway written. The spark that creates life might not be a rare event at all. It might be built into the process of planet formation itself. Still, the leap from chemistry to biology remains mysterious. On Earth, it took nearly 1 billion years for life to appear after the planet formed. Once it did, it diversified quickly, evolving from simple cells into complex organisms. Evolution favours adaptation, and time provides endless chances for success. If life can start somewhere once, it can start elsewhere again. The challenge isn't possibility, it's distance. The stars are too far apart for us to see such transformations up close. We can only infer, measure, and imagine. Among the billions of exoplanets discovered so far, a few stand out as especially promising. Proxima Centauri b, orbiting the closest star to the Sun, lies in its habitable zone. It's rocky, likely Earth-sized, and close enough that future telescopes might examine its atmosphere. The TRAPPIST-1 system, only 40 light-years away, has 7 planets, 3 of them in the zone where liquid water could exist. LHS 1140b, Kepler 442b, Tau 700d. The list grows with every survey. These worlds vary in composition and temperature, but each expands the map of potential habitability. Some orbit red dwarfs, where the risk of flares could threaten atmospheres. Others orbit quieter stars, offering more stable conditions. Every discovery adds a new variation to the question of how life might persist under different suns. Life elsewhere may not resemble anything familiar. On Earth, biology has adapted to every possible environment: boiling vents, frozen deserts, acidic lakes, deep caves, even clouds. Microbes survive in radiation levels that would destroy complex organisms, feed on minerals instead of sunlight, and remain dormant for millennia. Extremophiles show that life is flexible, opportunistic, and resilient. Given that adaptability, the range of possible life forms elsewhere widens beyond imagination. There could be ecosystems under ice crusts, microbial mats in methane seas, or organisms suspended in the upper atmospheres of gas giants. The variety of environments in the galaxy ensures that if life exists, it will be diverse. Even intelligence, though rare, might not be unique. The Drake equation, formulated in 1961, attempts to estimate the number of civilizations in our galaxy capable of communication. It multiplies factors such as the rate of star formation, the fraction of stars with planets, the fraction of planets that are habitable, the fraction where life arises, the fraction where intelligence develops, and the lifespan of technological civilizations. Each term carries uncertainty, but the framework helps define the question. Depending on how optimistic or conservative the values are, the number of detectable civilizations could range from 1, meaning us, to thousands. The equation doesn't answer the question, but it gives it shape. It reminds us that even if intelligent life is rare, The galaxy's size compensates for rarity. Billions of stars mean billions of chances. Despite that, the silence persists. We've listened for decades through radio telescopes, scanning for patterns that might indicate communication. The search for extraterrestrial intelligence, SETI, has detected nothing definitive. Some signals have sparked interest, like the WOW signal in 1977, but none have repeated or confirmed. This absence is sometimes called the Fermi paradox. If the galaxy is full of life, where is everyone? The answers may be practical rather than philosophical. Civilizations might be transient, lasting only a short time before fading. The distances between stars might be too vast for meaningful communication. Or perhaps life exists in forms that don't use technology as we understand it. Silence doesn't mean emptiness. It might simply mean difference. It's also possible that the search itself needs patience. On a cosmic timescale, humanity has only just begun listening. Our radio signals have been leaking into space for a century, barely a fraction of a heartbeat in galactic terms. They've reached only a few dozen light years, a tiny sphere within a galaxy 100,000 light years wide. If others are listening from farther away, they won't hear us for millennia. And if they transmitted in a different era, their signals might have passed by long before we were here to detect them. Communication across light years requires both timing and coincidence, and the odds of overlap are small. Still, the search continues, not out of expectation but out of curiosity. In the meantime, we explore indirectly. We look for traces of life in the atmospheres of exoplanets, in the ice of moons, in the chemistry of comets. Every discovery of complexity adds weight to the possibility that life is a natural outcome of the universe's laws. The ingredients are everywhere. Organic molecules in space, energy sources on planets, stability over billions of years. The Milky Way is not hostile to life. It's full of environments where it could arise. The question isn't whether life exists elsewhere, but how many variations of it do. The thought of life among the stars changes how we see our own. It shifts perspective from isolation to continuity. Earth is not separate from the cosmos. It's one of its experiments. The same forces that shaped our planet shape all others. The chemistry that began in interstellar clouds continues inside living cells. Life isn't a miracle imposed on matter. It's a property that matter expresses when conditions allow. The stars don't just host worlds, they host possibilities. Each planet is a new test of nature's creativity. If there are living worlds scattered across the galaxy, most of them are probably microbial. Complex life may be rare, intelligence rarer still, but microbes are resilient, adaptable, and ancient. They can survive radiation, vacuum, and extremes of heat and cold. Some scientists believe they could travel between worlds, hitching rides on meteorites or comets, a process called panspermia. If so, the galaxy might not only be full of life, but interconnected by it. Microbes from one system could seed another, spreading biology as naturally as starlight spreads energy. Over billions of years, that exchange could create a web of living matter, extending across the Milky Way. Whether that web exists or not, the implications are profound. To know that life has taken hold elsewhere would mean that the universe is fertile by nature. To find even a single microbe beyond Earth would redefine biology from a local phenomenon to a cosmic one. And if we were to find intelligent life, beings who have also looked up and wondered, it would redefine humanity's place entirely. The search for life among the stars is as much about understanding ourselves as it is about finding others. Life, wherever it exists, is fragile yet persistent. It adapts, endures, and evolves. It turns chemistry into memory, energy into meaning. The galaxy provides the raw materials, life provides the pattern. Somewhere, perhaps, under another sun, another species might be asking the same questions, wondering if they are alone, measuring faint signals, building telescopes, listening to the dark. If they exist, they are part of the same story we are. the story of matter learning to reflect on itself, to think, to feel curiosity. When you look at the stars, you are seeing the conditions for life written across the sky. Every one of those lights represents a potential home, a set of variables arranged just differently enough to produce endless possibilities. Some will be sterile, some will bloom, some will remain quiet, others will awaken. The galaxy is not a single experiment but a laboratory of billions. Each star is an opportunity for life to find a new form. The silence we hear is not emptiness. It's the sound of time waiting for us to listen long enough to understand it. When people ask how many solar systems there are in our galaxy, they usually expect a number, something measurable, something to hold on to, but the truth is that there isn't one, not exactly. The Milky Way doesn't lend itself to simple counting. It's a structure in constant motion, a living, shifting field of stars, planets, and gas that defies fixed totals. You can estimate, model, and approximate, but the moment you try to define the number, the galaxy has already changed. Somewhere, a new star has formed, and somewhere else, another has died. A planet has been captured, or lost, or shattered. The number you thought you had dissolves into flux. What we can say, though, is that whatever the number is, it's vast beyond imagination, a value that hovers between the measurable and the infinite. The idea of counting solar systems is appealing because it makes the cosmos feel tangible. We're used to putting quantities on things. How many stars? How many galaxies? How many worlds? But the scale of the Milky Way stretches that instinct to its breaking point. Our galaxy alone contains hundreds of billions of stars, perhaps more. Observations from missions like Gaia and Kepler suggest that nearly every star has at least one planet, and many have several. That means there could be hundreds of billions of solar systems, each a distinct arrangement of planets, moons, asteroids, and dust, each following its own path around its parent star. The galaxy, seen this way, becomes a vast ocean of systems, overlapping and intermingling, each a small story within a greater whole. The numbers themselves are astonishing. Kepler's data, combined with later surveys, led astronomers to estimate that there are roughly 1 to 2 planets for every star in the Milky Way. That alone suggests over 400 billion worlds, perhaps more if smaller planets and rogue ones are included. But even that doesn't tell the full story. A solar system is more than a count of planets. It's an arrangement, a gravitational pattern, a miniature cosmos. Each one is unique. Some have a single planet hugging close to the star, while others have dozens of bodies spread across wide orbits. Some contain asteroid belts or rings, others none. If you tried to assign each system a number on a list, you'd be cataloguing not just objects but relationships, the invisible geometry that holds them together. The Milky Way's disk is about 100,000 light-years across and roughly 1,000 light-years thick. Within that volume, stars are unevenly distributed. They cluster in the spiral arms, in dense star-forming regions, and in smaller groups scattered throughout the disk. In some areas, like the galactic core, the density of stars is so high that solar systems can almost brush past each other. In others, like the outer rim, the stars are sparse, separated by dozens of light years. To even begin to count solar systems, you'd need to account for that distribution. But stars move. They drift relative to one another, orbit the galactic center, and occasionally interact gravitationally. Systems can be disrupted, merged, or ejected. Over billions of years, the population changes constantly. Counting, then, becomes less about totals and more about understanding proportions. How common are stars with planets? How many of those planets are large, small, rocky, gaseous, habitable, or barren? The answers are statistical. Observations from Kepler showed that small planets, especially those between the size of Earth and Neptune, are the most common. Giant planets like Jupiter are rarer, but not unusual. Planets in the habitable zone, that delicate range where liquid water might exist, are less common, but still abundant in absolute numbers. When you multiply those probabilities by the number of stars in the galaxy, you get quantities that are staggering. Even conservative estimates yield tens of billions of potentially habitable planets. It's not a single number. It's a range, a scale, a probability field. In the human mind, large numbers eventually lose meaning. We can visualize 10 or 100, even 1,000, but beyond that, scale becomes abstract. A billion is not something we can picture. Yet the galaxy requires numbers on that scale just to describe its basics. 400 billion stars, 2 trillion planets, 100,000 light-years across. When you try to compress those figures into comprehension, the brain simply stops trying to measure and starts to feel. That transition from calculation to awe is where astronomy meets philosophy. The number of solar systems in our galaxy is less an equation than a perspective. It tells us that the cosmos is fertile, prolific, and constantly active. Even the process of estimation reveals how intertwined everything is. To count planets, you count stars. To count stars, you map the galaxy. To map the galaxy, you measure light, distance, and motion. Every step connects you to the next, until you realize that counting isn't about inventory. It's about participation. When astronomers measure how many systems there might be, they are describing the structure of the galaxy itself, and by extension, our place in it. The answer becomes not a fixed number, but a reflection of the galaxy's rhythm, a snapshot of how many systems exist right now, in this moment, in this phase of its life. That rhythm is slow but continuous. The Milky Way creates new solar systems every day. In the star-forming regions scattered along its spiral arms, vast clouds of gas collapse, ignite, and form new stars. Around those newborn stars, disks of dust flatten and swirl, creating planets. Elsewhere, old stars die, shedding material back into space to feed the next generation. Every atom in our bodies once belonged to some earlier cycle, forged in the heart of a star, scattered by an explosion, collected again into the matter that became Earth. The galaxy is not a static collection of systems, but an ongoing process of creation and recycling. Any attempt to count solar systems is really a snapshot of that process frozen in time. The moment you finish counting, the number has already changed. When scientists model how many solar systems there are, they often express their results as ranges and probabilities. They speak of occurrence rates, the fraction of stars with planets, the average number of planets per star, the proportion of certain types. The values vary depending on the methods used. Transit observations favour planets close to their stars, while radial velocity surveys detect larger masses. Direct imaging captures only a few wide-orbit giants. Each method reveals part of the truth, but not all of it. Combining them builds a statistical picture. Roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. Multiply that by the number of such stars, and you get something on the order of tens of billions. But those are only Earth-sized planets in habitable zones, a narrow slice of what exists. Expand the criteria to all planets of all sizes and types, and the total grows into the hundreds of billions. It's easy to lose track of meaning in such numbers, but sometimes meaning comes back in surprising ways. Each system, no matter how distant or insignificant it might seem, represents a potential for complexity. Planets are not mere statistics, they are environments. Some will be frozen wastelands, others scorched deserts, others swirling oceans or gas giants with dozens of moons. Some will remain stable for billions of years, others will dissolve after brief bursts of chaos. Each contributes to the galaxy's total inventory of worlds, and each is a unique outcome of the same physical laws that made our own. Counting them isn't just an exercise in astronomy, it's an act of recognition, of acknowledging that the cosmos doesn't produce in isolation, but in abundance. If we imagine trying to visualize the galaxy as a whole, we might think of it as a luminous disk filled with stars, like a cloud of fireflies frozen in motion. But between those stars are the planets, countless dark spheres invisible to the eye. The light you see from the Milky Way is only part of its reality. The majority of its material exists in forms that don't shine. Planets, dust, gas, dark matter, all contribute to the total structure. When we speak of how many solar systems there are, we're also acknowledging that most of the galaxy is invisible, known only through inference. Even the stars themselves, the ones we can see, represent only a fraction of the whole. The galaxy is made not just of visible light, but of everything light passes through. Astronomers sometimes describe the galaxy as having a planetary occupancy rate. It's a way of expressing how efficiently it turns material into worlds. The rate is high. Planet formation appears to be the natural consequence of star formation. Whenever a star ignites, a disk forms and planets follow. That means solar systems are not exceptional outcomes. They are standard. The galaxy is not sparsely populated. It's crowded. The spaces between stars are filled with orbits, paths, and histories. To count solar systems is to count inevitabilities. What makes the question so compelling is its mixture of simplicity and enormity. It sounds like something with an answer, a number, a total. But each attempt to fix that number turns into a journey through scale, process, and time. The Milky Way has existed for over 13 billion years. During that time, it has built and dismantled uncountable systems. Some of the oldest stars in its halo formed before planets were common, when the universe lacked heavy elements. As generations of stars lived and died, those elements accumulated, making planet formation easier. The current galaxy is more planet-rich than it has ever been. If you were to trace the history of solar systems over time, you'd see an exponential curve. Few at first, then many, then more, until the sky became saturated with worlds. The number, whatever it may be, isn't static because the galaxy itself isn't static. It's like asking how many waves are in the ocean. The answer depends on when you look. Each moment brings a new crest and a new trough. The galaxy's stars move in orbits that take hundreds of millions of years, and along those paths they create and lose worlds. Supernovae clear regions, gravity reshapes them, and new generations fill the gaps. Counting solar systems is like counting breathing, an act that measures life through motion. When scientists discuss these figures, they often hedge their statements. Hundreds of billions becomes the safest phrase. It's honest, flexible, and true to the uncertainty of the data. It encompasses the known and the unknown, the visible and the hidden. Within that phrase lies every possibility, from the well-measured planets we've detected to the theoretical ones we may never see. It includes systems like ours, and systems utterly unlike it. It includes those bound to stars and those drifting free. It includes everything that gravity can hold together for long enough to matter, and yet there's something profound about knowing that even our best estimates come close to infinity. If the galaxy contains hundreds of billions of systems, and each system contains multiple worlds, and each world contains billions of individual features, mountains, seas, storms, valleys, then the total number of places that exist right now defies comprehension. It's a number that exists only in concept, not in calculation. When you reach that scale, mathematics becomes poetry. The act of counting turns into the act of wondering. In that sense, asking how many solar systems there are is not really about arithmetic. It's about orientation. It's about understanding where we fit within the galaxy's structure. One small system among billions, neither central nor peripheral, ordinary yet extraordinary, simply by existing. The number doesn't define us, it contextualizes us. It reminds us that we are part of something too vast to measure and yet simple in its repetition. Stars form, planets form, systems evolve, and the process continues endlessly. Even if we could somehow list every solar system, the list would never be complete. Time itself would erase it. Stars would die, new ones would appear, planets would shift. The universe refuses to hold still long enough for a census. That's not a failure of measurement, it's the essence of its design. The Milky Way is not a static gallery of lights, but a dynamic organism, breathing through creation and destruction. Its number of systems is not a constant, but a pulse. When we try to express that pulse in words or digits, we do it knowing that the answer will always exceed us. Hundreds of billions is an approximation, but it's also a gesture, a way of acknowledging scale while accepting mystery. The number isn't a number because it doesn't stop. It grows, changes, and eludes definition, just like the galaxy itself. Somewhere, right now, a new star is igniting, a disk is forming, and the first grains of dust are beginning to stick together. Another solar system has just been born, adding one more to a count that was already beyond counting. And while that happens, we orbit quietly within our own small system, one of the many, part of the total that cannot be defined but can always be imagined. The galaxy continues to build its uncountable architecture, one world at a time, and we, living on one of them, are witnesses to a process that never ends, a number that never resolves, a universe that never stops adding to itself. When you look up at the night sky, what you're seeing isn't somewhere else. You're looking into the structure that you're already inside of. Every star above you, every faint glimmer and cloud of light, is part of the same system you belong to. The Milky Way isn't a backdrop, it's home. The air you breathe, the atoms in your body, the sunlight that warms your face, all come from the same matter that fills that galaxy. It's easy to think of space as something distant, something unreachable, but in reality you are already there. You're within it now, orbiting a star that itself orbits the galactic center, surrounded by countless other suns doing the same. You're not on the outside looking in, you're inside looking out. Our solar system drifts through the Orion Spur, a quiet lane between the Milky Way's spiral arms. The sun moves at about 200 kilometers per second, completing one revolution around the galaxy roughly every 230 million years. It's an orbit that's carried our system through regions of dense star formation, past dark clouds of dust, and into empty stretches of interstellar space. The Earth, carried along for the ride, spins and circles in its familiar pattern, tracing a smaller orbit within a much greater one. As you sit here, reading or listening, you're part of that movement, part of a planet spinning at 1,000 miles per hour, orbiting a star racing around the galactic center in a pattern that's been ongoing since before any life existed here. The stability you feel is motion too slow to sense. That motion connects you to everything else in the galaxy. The light that reaches your eyes from the stars took years, sometimes centuries, to get here. When you see the faint band of the Milky Way stretching across the sky, you're looking at light that's been travelling through space for thousands of years. Each point of brightness represents a place in motion, a star that may already have changed or even disappeared, but whose light is still crossing the gulf of space toward us. The galaxy doesn't exist all at once. We see it in pieces of time, layered and delayed. Every star is a story that began long before you looked at it. From this planet, we measure the galaxy as an object, something we can describe and chart. We speak of distances, of masses, of ages. We give names to its parts, the bulge, the arms, the halo. But to live within it is to be part of something that can't be reduced to measurements. You exist within a structure that's made of the same materials as you, moving on the same currents of gravity and time. The iron in your blood was forged in a supernova. The calcium in your bones, the carbon in your cells, the oxygen in your lungs, all came from stars that lived and died billions of years before the sun was born. You're not made of something separate from the galaxy. You're made of it directly. If you could rise far above the galactic plane, you would see the Milky Way as a glowing disk, its spiral arms wrapping around a bright core. From that distance, our sun would be invisible to the eye. Yet within that faint point, entire histories are unfolding. Oceans rising and falling, continents shifting, species evolving, civilizations building and dissolving. The scale difference is difficult to grasp. The galaxy is so large that light takes 100,000 years to cross it. But even at that scale, you are not insignificant. Every bit of life here, every thought, every act of observation is part of the galaxy's ongoing process. The matter that became aware of itself is not outside of nature. It is nature recognizing itself. As you imagine that view, the glowing disk, the spiral arms, the vast void surrounding it, remember that it's not something separate. The stars are not distant lights above you. They are your environment, the extended form of the same system that sustains you. You live within the Milky Way the way a cell lives within a body. You're influenced by its gravity, its radiation, its chemistry. The galaxy shapes the light that reaches you, the time that passes, the path that your planet takes through space. Whether you think about it or not, you are always inside it, part of its field, moving with it as it moves through the larger universe. In that larger context, the Milky Way itself is just one among billions of galaxies. From even farther away, it would appear as a small, faint spiral, one speck among clusters and filaments stretching across the cosmos. But within it, every star has a gravity of its own, every system a rhythm, every world a history. The same physics that holds our solar system together holds the galaxy together. The same processes that form stars here form them everywhere. You are part of a pattern that repeats across the universe, scaled from the atomic to the galactic. The difference is only one of size and time. Here, on this planet, life developed in the narrow zone where energy and matter could find balance. For billions of years, the Earth has orbited steadily, maintaining the temperatures and conditions that allowed complexity to grow. That balance, fragile as it seems, is not accidental. It's the result of countless interactions, the pull of the moon stabilizing our tilt, the gravity of Jupiter diverting comets, the chemical resilience of our atmosphere, the heat of the sun moderated by distance. Every one of those factors traces back to the galaxy's formation, the metals in the Earth's crust, the water in its oceans, the carbon in its air. All were shaped in earlier generations of stars. Your presence here, your awareness of that fact, is a continuation of that same sequence. The light that leaves Earth now will travel outward through the galaxy long after we're gone. It will move through interstellar dust, through the arms of the Milky Way, through the thin plasma between stars. In 100,000 years, it will have barely crossed the disk. In a billion, it will still be moving, carrying a trace of what happened here. The light of a small planet around a middle-aged star. Somewhere far away, perhaps another civilization will detect that light and wonder what kind of world produced it. To them, we will be part of their galaxy, just as they are part of ours. In the long lifetime of the Milky Way, stars are born, live and die by the hundreds of millions. The galaxy continually reshapes itself through gravity, through time, through motion. Spiral arms shift, clouds condense, clusters dissolve. Over billions of years, our own sun will change too. It will exhaust its hydrogen, expand into a red giant, and eventually shrink into a white dwarf. The planets will change or vanish, their orbits altered, their surfaces consumed or frozen. But the matter will remain. The dust of our solar system will join the interstellar medium, contributing to the next generation of stars and planets. The galaxy recycles itself endlessly, turning old matter into new beginnings. Even when this solar system is gone, its materials will continue the pattern, part of the same cycle that made it in the first place. It's possible to think of the Milky Way as an organism, not in a biological sense, but in the way it grows and evolves. It consumes and produces, creates and dissolves, always maintaining balance between chaos and order. Within it, everything interacts. Stars tug on each other, clouds collide, supernova enrich surrounding space with elements. Out of that complexity comes simplicity again: light, motion, and structure. The galaxy maintains itself through the same rules that govern atoms and orbits. When you look up and see its faint band across the sky, you're looking at that equilibrium made visible. The night sky itself is a kind of mirror. You can see stars, but what you're really seeing is context. Each point of light is a reference point that connects you to something larger. The faintest stars visible to the naked eye are hundreds or thousands of light years away. The brightest are only tens. Some of them may already have burned out, but their light continues to travel. The galaxy's history is written in that light, a history of creation, destruction, and renewal. Every photon that reaches you has been on a journey, moving through space unimpeded until it encounters your eyes, ending a story that began before humans existed. Standing on this planet, you can feel small compared to that vastness, but small isn't wrong. Scale doesn't determine meaning. You're a result of the same forces that shape galaxies, operating on a smaller canvas. The hydrogen in your body once existed in the early universe, unbound and simple, until stars forged it into heavier elements and released it again. You are the continuation of that process, conscious matter arranged in patterns that can recognize patterns. The galaxy is not above you, it is within you. The same physical laws that keep the Earth in orbit also sustain the chemistry that keeps you alive. Gravity holds both your body and the stars in their respective places. You are made of what the Milky Way is made of. It's easy to forget that connection when you live surrounded by boundaries, walls, cities, maps, coordinates. But those are human frames imposed on something without edges. The Milky Way has no border, no line where one part stops and another begins. It's continuous, blending into the intergalactic medium that connects it to other galaxies. Even space itself is not empty. It's filled with the remnants of everything that has ever existed, diffused but persistent. You live in that continuum every moment of your life. The air around you, the light from the sun, the particles moving through your body, all are parts of the galaxy in motion. When you think about your position here, it's natural to ask where the center is. In the galaxy, the center is defined by gravity, by the dense cluster of stars surrounding the supermassive black hole Sagittarius A. But in another sense, there is no single center that matters more than any other. Every point, every star, every planet is its own center from its own perspective. You are as central to your experience of the galaxy as any other observer anywhere. The Milky Way has no front or back, no up or down. It's an expanding, rotating, evolving field. From here, you occupy one of its countless vantage points, just as others might from theirs. If you could see it from outside, the Milky Way would appear as a calm spiral of light, its arms glowing with star-forming regions, its core dense and bright. From within, it's a tapestry of points and darkness, of glowing nebulae and empty stretches of space. The galaxy feels still because its movement is vast. It changes so slowly that human lifetimes barely register. But if you could watch it sped up, billions of years condensed into moments, you'd see it breathe. Stars would form and fade, arms would twist and unwind, collisions would reshape its shape. That motion is ongoing even now, at scales we can't sense. Through that slow motion, the sun continues its orbit, and the Earth continues its smaller one. You, in turn, move with it. Every second, you travel thousands of kilometers through the galaxy. Every minute, you move deeper into a space that will never be the same again. The stars above you are not fixed points, but companions on the same journey. The galaxy carries all of us together, stars, planets, dust, and light, bound by the same gravity, moving through the same cosmic neighborhood. You are never still within it, and yet, within that motion, there is peace. Somewhere, beyond the reach of the naked eye, new solar systems are forming. Dust is collapsing, Light is igniting, and new planets are taking shape. Somewhere else, stars are dying, scattering elements back into space. The Milky Way never stops. Its story doesn't have a clear beginning or end. It has cycles, transitions, and continuations. To live within it is to exist inside one of those continuations. You're part of the galaxy's current phase, a moment between what was and what will be. When you think of yourself within that structure, remember that awareness itself is part of the galaxy's evolution. You are the means by which the Milky Way perceives itself, the way it has developed to understand what it is. You're a product of the same physical laws that made stars, but you carry within you the ability to ask why they exist. That capacity, curiosity, is not outside nature. It's one of its outcomes. When you look at the night sky, when you wonder about what's out there, the galaxy is reflecting on itself through you. You exist, here, now, in the Milky Way. The stars above you, the planet beneath you, the light around you, all part of one continuous reality. You are made of it, carried by it, and connected to it. The galaxy doesn't know boundaries between you and itself. It holds you as one of its smallest but most intricate creations. And as you breathe, think, and feel the quiet of night, you are not separate from the stars you see. You are their continuation, their descendant and their observer all at once, the galaxy aware of its own existence in the form of you.